You're trapped in an elevator that's endlessly falling. Not to your doom, but in an infinite loop. Every 7.8 seconds, you reset to the top. Your watch still ticks normally, but you're stuck in this endless cycle. Sound impossible? Well, scientists have created something just like this. They're called temporal crystals, and they're breaking everything we thought we knew about time itself. In 2012, Nobel laureate Frank Wilczek proposed the seemingly impossible, a system that could move while remaining in its lowest energy state, creating a pattern that repeats in time, just as the atomic structure of a diamond repeats in space. The physics community initially rejected this idea as it appeared to violate basic thermodynamic principles. After all, perpetual motion machines are impossible, and anything that moves must consume energy. But nature, as it often does, had a surprise in store. In 2016, researchers at the University of California, Berkeley, and the University of Maryland independently created the first time crystals. They used two fundamentally different systems, one employing a chain of trapped ions, the other using defects in diamond, but both demonstrated the same extraordinary property, a system that cycled through a pattern of states at a fixed period, even without continuous energy input. The key to understanding temporal crystals lies in quantum mechanics and the concept of symmetry breaking. Just as spatial crystals break translational symmetry in space, the atoms aren't evenly distributed, but form regular patterns. Time crystals break time translation symmetry. When you hit a time crystal with a laser pulse at a particular frequency, it responds by cycling at a different, fixed frequency, typically half the driving frequency. It's rather like having a jelly that, when wobbled once per second, naturally wobbles back and forth every 2 seconds instead. This behavior seems to defy our understanding of thermodynamics. Systems should eventually settle into their lowest energy state and stop moving. This is why perpetual motion machines are impossible. But time crystals manage to keep moving while remaining in their ground state, thanks to the bizarre rules of quantum mechanics and the protective effects of many-body localization, a phenomenon that prevents the system from absorbing energy and heating up. The implications of temporal crystals extend far beyond mere scientific curiosity. They represent an entirely new phase of matter, one that exists not just in space, but in time. This discovery has potential applications in quantum computing, where maintaining coherent quantum states is crucial. A time crystal's ability to remain stable and periodic without consuming energy could provide new ways to store and process quantum information. The connection between time crystals and other physical phenomena reveals deeper patterns in nature. Consider superconductivity, where electrons move through a material with zero resistance. Both phenomena involve quantum effects, manifesting at a macroscopic scale, creating states of matter that seem to violate our classical intuitions. The key difference is that superconductors break gauge symmetry, while time crystals break time translation symmetry. The philosophical implications are equally profound. Time crystals challenge our understanding of time itself. If a system can cycle through states perpetually while remaining in its ground state, what does this tell us about the nature of time and energy? It's rather like discovering a clock that ticks forever without needing winding, forcing us to reconsider our most basic assumptions about the arrow of time and the inevitable march toward entropy. Modern experiments continue to push the boundaries of what's possible with temporal crystals. In 2021, researchers created the first time crystal using Google's Sycamore quantum computer, demonstrating that these strange states can exist in purely digital systems. This breakthrough suggests that time crystals might play a crucial role in future quantum technologies, offering new ways to maintain stable quantum states in computing systems. Coming back to our elevator thought experiment, perhaps it's not so different from a time crystal after all. Both systems repeat their states precisely, maintaining order despite seeming to violate our intuitions about energy and time. The key difference is that while your endless elevator ride would require constant energy input to maintain its cycle, a time crystal achieves its perpetual motion through the fundamental properties of quantum mechanics. And so we find ourselves facing one of physics' most elegant paradoxes, a system that moves while remaining still, that changes while staying the same, that keeps time by breaking time itself. In the end, temporal crystals remind us that the universe is not bound by our expectations, but by the deeper patterns that emerge when we push the boundaries of what we think is possible. Psychological time distortion. You've been clinically dead for 6 minutes, yet you've somehow experienced an entire lifetime, complete with marriage, children, and grandchildren, in those fleeting seconds before resuscitation. Your perception of time has completely untethered from reality, and you're not alone in this unsettling experience. The phenomenon of psychological time distortion has puzzled scientists since the 1860s, when Gustav Fechner first attempted to measure subjective time experiences in his groundbreaking work, Elements of Psychophysics. He discovered something remarkable. Our internal clock bears little resemblance to the mechanical ones we've built to measure time's passage. In 1979, neuroscientist Benjamin Libet conducted his famous experiments at the University of California, revealing that our conscious awareness of decisions lags behind our brain's actual decision-making by about 200 milliseconds. This temporal gap between neural activity and conscious experience opened up profound questions about free will and the nature of time perception itself. But the real breakthrough in understanding time distortion came from David Eagleman's 2005 experiments at Baylor College of Medicine. He had participants experience freefall drops while trying to read a special chronometer strapped to their wrists. The results were astonishing. During moments of intense fear or excitement, people perceived time moving up to 1.5 times slower than normal, yet their ability to actually process information didn't increase. Time wasn't really slowing down. Their brains were simply recording more memories during these high-stakes moments. This brings us to the central paradox. Our experience of time isn't fixed at all, but rather exists as a flexible construct created by our brains. When you're engaged in stimulating conversation or absorbed in a compelling task, hours can feel like minutes. Conversely, watching paint dry or waiting for exam results can make minutes feel like hours. This malleability of perceived time reveals something profound about consciousness itself. The neuroscience behind this is rather elegant. Our brains don't actually track time like a clock does. Instead, they create our sense of time's passage through a complex interaction between the striatum, which handles rhythm and timing, and the insular cortex, which integrates various sensory inputs into our conscious experience. When these systems encounter novel or threatening situations, they shift into a higher gear of information processing, creating the illusion of time dilation. This mechanism served our ancestors well. In life or death situations, perceiving time as moving slower allowed for more detailed processing of crucial information. A predator's attack might seem to unfold in slow motion, giving our ancestors precious extra moments to react. But this same system can work against us in modern life, particularly during states of anxiety or depression, where time distortion often becomes a source of suffering. The implications extend far beyond individual psychology. Einstein's theory of relativity showed us that time itself is not absolute, but relative to the observer's frame of reference. What's fascinating is how our subjective experience of time mirrors this physical reality. Time truly does move at different rates depending on the observer's state, both mentally and physically. This convergence of physics and psychology raises profound questions about the nature of consciousness and reality. If our experience of time is so malleable, what other aspects of our perceived reality might be equally flexible? The philosophers Daniel Dennett and David Chalmers have argued that consciousness itself might be better understood as a kind of user interface, a way for our brains to organize and make sense of information rather than a direct window onto reality. Recent research in quantum mechanics has only deepened these questions. The Wheeler-DeWitt equation, sometimes called the timeless equation, suggests that at the quantum level, time might not exist at all. Our entire experience of time's flow could be an emergent property of consciousness rather than a fundamental aspect of reality. Like those 6 minutes of clinical death that contained a lifetime of experiences, our perception of time reveals something fundamental about the nature of consciousness itself. Time isn't flowing past you like a river. You're actively constructing your experience of its passage moment by moment, your brain weaving together memories, expectations, and sensory inputs into what feels like a continuous stream of experience. Perhaps then, the time shown on our watches was never the real time at all, just one of many possible ways to measure a phenomenon that exists as much in our minds as in the physical world. The Maxwell demon problem. Your consciousness has been hijacked and imprisoned in a quantum cell 1/1000th your size, where a demonic gatekeeper is committing the ultimate crime against physics. This atomic anarchist, armed with nothing but an impossible trapdoor, is methodically shredding the universe's most sacred laws. And you're the only witness to this molecular mutiny. This thought experiment, introduced by James Clerk Maxwell in 1867, would come to be known as Maxwell's demon, and it presented physics with one of its most enduring paradoxes. Maxwell first proposed this idea in a letter to Peter Guthrie Tait, suggesting that a very observant and neat-fingered being could potentially sort molecules by their speed, creating a temperature difference without expending energy, something that should be impossible according to thermodynamics. The demon's apparently simple task raises profound questions about the nature of information, entropy, and the fundamental limits of physical systems. To understand why this tiny daemon caused such an uproar in the physics community, we need to grasp what makes the second law of thermodynamics so crucial. This law states that the total entropy, essentially the measure of disorder in a system, always increases over time. It's why hot coffee cools to room temperature, why ice cream melts on a summer day, and why you can't unscramble an egg. But Maxwell's demons seem to offer a way around this universal principle. By sorting molecules based on their speed, which correlates with their temperature, the demon could create order from disorder without any apparent energy input. It would be like having a self-organizing bookshelf that automatically sorted volumes by height, or a room that spontaneously tidied itself, a clear violation of entropy's ever-increasing nature. The implications stretched far beyond simple temperature differences. If Maxwell's demon could work, it would effectively create a perpetual motion machine, violating not just the second law, but our entire understanding of energy conservation. You could use the temperature difference between the two sides of the room to drive an engine, generating free energy from nothing but the demon's clever sorting. The resolution to this paradox wouldn't come until nearly a century later, through the work of multiple physicists, most notably Leo Szilard in 1929 and Rolf Landauer in 1961. Their insights revealed something profound. Information itself has a physical cost. The demon, in order to sort the molecules, must first obtain information about their speeds. This measurement process, combined with the need to store and erase this information from the demon's memory, inevitably generates entropy that at least equals the amount of order the demon creates. Landauer's principle specifically quantified this relationship, showing that erasing one bit of information must generate at least kTln2 energy and heat, where K is Boltzmann's constant and T is the temperature. The demon's memory, like any physical system, must eventually be reset to continue its work, and this erasure process produces enough entropy to satisfy the second law. This resolution connects to modern quantum computing, where information and physical reality intersect in fascinating ways. The energy cost of information processing places fundamental limits on computation itself, suggesting that even our most advanced computers must generate heat simply by manipulating bits. The demon also raises questions about consciousness and observation. What exactly constitutes a measurement? Does the demon need to be intelligent, or could an automated system perform the same task? These questions touch on quantum mechanics' measurement problem and the role of observers in physical systems. As you watch the demon at his endless task, sorting molecules with tireless precision, you might wonder about the nature of information itself. Every bit of knowledge about those molecular speeds comes with an energy cost. a fundamental tax levied by the universe on the act of knowing itself. The demon's paradox reveals that information isn't just abstract, it's physical, bound by the same laws that govern matter and energy. And so, our tiny doorman continues his work, no longer threatening to overthrow thermodynamics, but instead revealing deep connections between information, energy, and the fundamental nature of reality itself. The room remains bound by the second law, yet through this apparent paradox, we've gained profound insights into the price we pay for knowledge and the inescapable link between information and physical reality. Bernoulli effect anomaly. You're about to die. At least that's what your brain screams as a 40-ton semi-truck barrels past mere inches from your body at 70 miles per hour. But instead of being blasted away from the massive vehicle, your body is being inexplicably sucked toward the rushing metal wall like a moth to a deadly flame. This counterintuitive phenomenon, which has likely caused more than a few pedestrians to stumble, emerges from one of fluid dynamics' most misunderstood principles, the Bernoulli effect. The origins of this deadly dance with physics trace back to 1738, when Daniel Bernoulli's Hydrodynamic turned our understanding of fluid behavior on its head. His principle, that an increase in fluid velocity must correspond to a decrease in pressure, seems innocent enough on paper, but in reality, it creates situations so bizarre they border on the supernatural. That truck threatening to make you part of the pavement, it's creating a high-velocity air corridor along its side. Following Bernoulli's principle, this rushing air has lower pressure than the still air surrounding you. Nature, in its relentless pursuit of equilibrium, pushes you from the high-pressure zone toward the low-pressure death trap beside the truck. Ship captains learned this lesson the hard way when their vessels mysteriously crashed together in calm seas, pulled by these invisible forces. But here's where reality starts to bend even further. In 1964, Henri Coanda demonstrated something that would have made even Bernoulli question his sanity. When a fluid meets a curved surface, it doesn't just follow Bernoulli's rules, it becomes almost magnetic, clinging to the curve with an enthusiasm that defies common sense. Take a spoon under your kitchen tap. The water doesn't just fall straight down, but hugs the curve like a long-lost friend. This leads us to a paradox that kept aerospace engineers awake at night. According to pure Bernoulli calculations, many modern aircraft should be earthbound. The math suggests they'd need wings the size of football fields or engines powerful enough to rival small suns. Yet these metal birds soar through our skies daily, thumbing their noses at classical fluid dynamics. The resolution to this apparent impossibility reveals the humbling complexity of our universe. Bernoulli's principle isn't wrong, it's just part of a larger symphony of forces. Modern aircraft don't just rely on simple pressure differentials. They harness complex vortices, boundary layer interactions, and what engineers call dynamic lift, phenomena that would have been as alien to Bernoulli as smartphones would have been to Leonardo da Vinci, but the rabbit hole goes deeper. In 2008, University of Michigan researchers discovered something that sent shockwaves through the physics community. In certain microfluidic systems, fluids were observed moving from low pressure to high pressure regions, the equivalent of watching water flow uphill. This reverse Bernoulli effect didn't just bend the rules, it broke them entirely. The implications ripple through every field touching fluid dynamics. Consider your own circulatory system. Traditional Bernoulli effects suggest blood should behave one way in narrowed arteries, but reality shows something quite different. This might explain why certain cardiovascular conditions have baffled medical scientists for decades. Philosophically, these anomalies force us to confront uncomfortable truths about scientific understanding. Every equation we write, every principle we establish, comes with hidden asterisks and footnotes. Just as Newton's laws crumble at the quantum scale, Bernoulli's principle reveals its limitations in extreme conditions. So the next time a truck passes too close for comfort, and you feel that ethereal pull toward its rushing side, remember, you're not just experiencing a simple physical effect, you're witnessing one of nature's most elegant demonstrations that reality is always more complex than our equations suggest. In that moment of instinctive terror, you're connecting with a truth that has humbled scientists for centuries. The universe never stops surprising us. And perhaps that's the real anomaly. Not that Bernoulli's principle sometimes fails, but that we ever expected simple mathematics to fully capture the beautiful complexity of our physical world. Matter-Antimatter Asymmetry. You're the last human in existence, floating in an incomprehensibly vast void of nothingness, because the universe itself has completely annihilated. Not through heat death or big crunch. No, you're here because someone went back in time and perfectly balanced the amounts of matter and antimatter in the early universe, causing everything to destroy itself in a flash of pure energy. The fact that you're alive right now, reading this, is proof that something went wonderfully wrong 13.8 billion years ago. This cosmic accounting error might be physics' greatest stroke of luck. You see, in the earliest moments after the Big Bang, the universe should have created equal amounts of matter and antimatter. Every particle should have had its opposite twin, each electron paired with a positron, each proton with an antiproton. When matter meets antimatter, they annihilate completely, converting their mass into pure energy. Had perfect symmetry prevailed, everything would have cancelled out, leaving nothing but a universe filled with radiation. Yet here we are, made of matter, living in a matter-dominated universe. Somehow, for every billion pairs of particles and antiparticles that annihilated each other, one lonely particle of matter survived. This tiny imbalance, just one part in a billion, is responsible for everything we see today, every galaxy, star, planet, and living being. The search for an explanation led to the work of Andrei Sakharov in 1967. He outlined 3 conditions necessary for matter to dominate. The universe must have violated charge parity symmetry, operated out of thermal equilibrium, and broken baryon number conservation. While that might sound like scientific gibberish, it's really a recipe for cosmic survival. Think of it like a vast cosmic casino where particles and antiparticles are playing an endless game of roulette. The rules should be perfectly fair, giving each side equal chances of winning. But Sakharov suggested the casino itself might have been ever so slightly rigged in matter's favor, not through any deliberate choice, but through fundamental properties of physics itself. The Large Hadron Collider has shown us tiny examples of this matter favoritism in certain particle decays. But these known asymmetries are far too small to explain our universe's matter excess. It's as if we found evidence of the casino dropping a few extra chips on the matter side of the table, when we need to explain how matter walked away with the whole house. Some physicists have proposed that neutrinos, those ghostly particles that barely interact with normal matter, might hold the key. The theory of leptogenesis suggests that in the universe's first fraction of a second, super-heavy neutrinos decayed in a way that slightly favored matter over antimatter. It's a bit like discovering that while the visible games on the casino floor were mostly fair, there was a hidden high-stakes room where matter quietly accumulated its winning edge. Others looked to the Higgs boson, discovered in 2012, as a possible culprit. Perhaps during the electroweak phase transition, when the Higgs field gave mass to particles, the process wasn't quite as smooth as we thought. Like a cosmic card dealer with an unconscious tell, the universe might have revealed its preference for matter in the way this fundamental force broke its symmetry. The implications stretch far beyond mere particle physics. Our very existence hinges on this fundamental imbalance. If the asymmetry had been even slightly different, we might have ended up with a universe containing too little matter to form galaxies, or one where matter and antimatter regions remained separated, creating devastating boundaries of annihilation throughout space. This brings us to a rather uncomfortable possibility. Perhaps we're asking the wrong question. Instead of wondering why there's more matter than antimatter, we might need to ask why we observe a universe with any matter at all. The anthropic principle suggests that we can only exist in a universe where the matter-antimatter asymmetry worked out just right. So of course, that's the kind of universe we see. It's rather like questioning why Earth is at just the right distance from the Sun for liquid water. There might be countless other universes with different matter-antimatter ratios, but we can only find ourselves in one where matter won, by just enough to create the complexity needed for conscious observers. As you float here in this hypothetical void, contemplating the razor's edge of cosmic fortune that allowed matter to survive, perhaps there's a certain poetry in it all. That tiny imbalance, that cosmic accounting error, that 1 in a billion survival rate, it's written into every atom of your being. Thermodynamic time reversal. You're trapped in a universe where time has suddenly reversed. Your dead grandmother rises from her grave. Wars unfight themselves as bullets fly backward into gun barrels, and you watch helplessly as your own life rewinds toward your birth. According to the fundamental laws of physics, this scenario isn't just possible, it's exactly as valid as time flowing forward. Yet something profound prevents this cosmic rewind from ever occurring, and that something lies in a broken egg on your kitchen floor. The laws of physics maintain a peculiar indifference to time's direction. A film of 2 billiard balls colliding would obey Newton's laws perfectly, whether played forward or backward. Yet our world stubbornly refuses to work this way. Broken eggs don't reassemble, coffee and cream don't unmix, and yesterday steadfastly remains behind us. This asymmetry tormented Austrian physicist Ludwig Boltzmann in the 1870s, driving him to develop statistical mechanics in an attempt to reconcile the microscopic reversibility of physics with our macroscopic reality. Peer into the quantum realm, and you'll find nearly every fundamental equation treats forward and backward time as equals. The Schrödinger equation governing quantum states, Maxwell's electromagnetic ballet, even Einstein's gravitational field equations, all remain perfectly valid when time reverses direction. Only the weak nuclear force shows any preference, and this tiny asymmetry can't explain why your morning coffee won't spontaneously separate into black coffee and cream. The resolution lies in the mathematics of probability and the sheer numbers involved in everyday events. While each individual particle could reverse its course, coordinating the countless molecules in a broken egg to simultaneously backtrack their paths becomes an exercise in astronomical improbability. Boltzmann captured this through his revolutionary H theorem, introducing entropy as a measure of nature's tendency toward disorder. Think of a whole egg as a masterfully organized library where every molecule has its precise place. Smash it, and you've created countless shelves where those molecules could end up while still forming what we recognize as a broken egg. The mathematics shows that systems naturally drift toward these states of higher entropy, not because they must, but because there are vastly more ways to be disordered than ordered. This statistical tendency creates the thermodynamic arrow of time, the cosmic preference for disorder that shapes our entire experience of reality. It's not that time reversal defies physics. Rather, it defies probability on a scale that makes lottery wins look like certainties. You're more likely to see every air molecule in London randomly gather in one neighborhood than witness a broken egg spontaneously reassemble. But this explanation spawns an even deeper mystery. Why was our universe born in such an improbably ordered state? The fact that entropy can still increase today means the early universe must have been extraordinarily well organized. This observation led Roger Penrose to propose his Weyl curvature hypothesis in 1979, suggesting that time's arrow might be fundamentally etched into the gravitational conditions of the Big Bang itself. The plot thickens at the edges of black holes, where Stephen Hawking discovered that a black hole's entropy precisely matches its event horizon's surface area. This remarkable connection hints at profound links between thermodynamics, gravity, and time. Relationships that string theory and quantum gravity are still struggling to fully comprehend. These insights launch us into questions that transcend pure physics. If entropy must always increase, does this condemn our universe to an eventual heat death, a state of perfect disorder where no further change is possible? Physicists like Sean Carroll propose broader perspectives, suggesting our observable universe might be one region in a vast multiverse where entropy flows in both directions. The thermodynamic arrow of time isn't just an abstract concept. It's the reason you remember yesterday but not tomorrow, why causes precede effects, and why that egg on your floor remains stubbornly broken. It's a fundamental asymmetry woven into the fabric of our existence, determining the direction of every process from the cosmic to the mundane. So the next time something breaks, take a moment to appreciate that you're witnessing more than just destruction. You're observing one of the universe's deepest principles in action. In every shattered egg lies a window into the nature of time itself, reminding us that even in life's smallest accidents, we can glimpse the profound mysteries that continue to challenge our greatest minds. Classical Doppler effect. You're standing on a train platform when something peculiar catches your attention. The sound of an approaching train's whistle seems to rise in pitch, then suddenly drops lower as it passes by. Yet you know the train's whistle hasn't actually changed its note at all. What you're experiencing is one of physics' most elegant phenomena, one that not only explains this everyday occurrence, but also helped us understand the expansion of the universe itself. This shift in perceived sound frequency was first mathematically described by Austrian physicist Christian Doppler in 1842. In his groundbreaking paper on the colored light of double stars and certain other stars of the heavens, Doppler wasn't actually focused on sound at all. He was attempting to explain the different colors observed in binary star systems, but his mathematical insights would prove far more universal. The mathematics behind the effect is surprisingly straightforward. When a source of waves, whether sound, light, or water, moves relative to an observer, the perceived frequency changes. If the source moves toward the observer, the waves become compressed, increasing their frequency. When moving away, the waves stretch out, decreasing their frequency. It's rather like a cosmic accordion, playing different notes depending on its motion. The first experimental verification of Doppler's theory came in 1845 when Dutch scientist Christoph Buys-Ballot conducted what must have been quite a spectacle. He placed a group of musicians with perfect pitch on a moving train and had them play a specific note. Another group of musicians with perfect pitch stood along the tracks, listening and recording the apparent pitch as the train passed. The results perfectly matched Doppler's predictions. But the implications of this effect extend far beyond train whistles and passing sirens. In 1929, Edwin Hubble used the Doppler effect to make one of astronomy's most significant discoveries. By observing the light from distant galaxies, he noticed their spectra were systematically shifted toward the red end of the spectrum, a phenomenon now known as redshift. This observation provided the first evidence that the universe is expanding, fundamentally changing our understanding of cosmic evolution. The mathematics reveals something rather remarkable about the nature of waves themselves. The effect doesn't care about the type of wave involved. Sound, light, water, or even gravitational waves all exhibit the same behavior. This universality points to something fundamental about the way waves propagate through space and time. The effect has found practical applications in numerous fields. Medical ultrasound devices use it to measure blood flow in arteries. Police radar guns catch speeding drivers by measuring the Doppler shift of reflected radio waves. Weather radar systems track storm movements by detecting the shift in waves reflected off rain droplets. Even GPS satellites must account for relativistic Doppler effects to maintain their accuracy. One particularly intriguing application emerges in the search for exoplanets. When a planet orbits a star, it causes the star to wobble slightly. This wobble creates a tiny Doppler shift in the star's light, sometimes as small as a few meters per second. By measuring these minute shifts, astronomers can detect planets we can't directly observe, leading to the discovery of thousands of worlds beyond our solar system. The effect also raises some fascinating philosophical questions about perception versus reality. The frequency change we observe is entirely real from our reference frame, yet from the perspective of the source, nothing has changed at all. It's a reminder that many aspects of our experience depend critically on our point of view. What's true from one perspective may be different from another, yet both perspectives are equally valid. There's a certain poetry in how this simple observation of changing pitch has led to such profound insights about the nature of our universe. From the daily experience of passing sirens to the grand expansion of cosmic space, the Doppler effect weaves together the mundane and the sublime through the elegant mathematics of wave motion. The next time you hear an approaching siren, remember, you're not just experiencing an acoustic curiosity, you're witnessing a phenomenon that helped us understand the very expansion of space itself, all through the subtle shift of waves as they journey from source to observer, playing the universe's own symphony of motion and perception. Information conservation law. You're standing in front of an enormous shredder at a top-secret government facility, holding the only copy of classified documents containing vital national security information. As you feed the papers through, reducing them to confetti, a disturbing thought strikes you. You haven't actually destroyed the information at all. In fact, according to the fundamental laws of physics, it's impossible to truly destroy information. Every single bit of data about those documents, down to the precise position and momentum of each atomic particle, must still exist somewhere in the universe. This seemingly absurd conclusion emerges from one of physics' most profound principles, the law of information conservation. First formalized by Leonard Susskind and Gerard 't Hooft in the early 1990s, this principle states that information can never be lost from the universe. It can only be transformed or scrambled into different forms. This revelation arose from their work on the black hole information paradox, a problem that had puzzled physicists since Stephen Hawking's groundbreaking work on black hole radiation in 1975. The mathematical foundations trace back to 19th century physicist Ludwig Boltzmann's H-theorem and the development of statistical mechanics. Boltzmann showed that while systems tend toward increasing entropy, the underlying physical laws are reversible, meaning information about initial conditions must be preserved even if practically inaccessible. This concept found its quantum mechanical expression in the unitary evolution of wave functions, described by the Schrödinger equation. But what does this actually mean in practice? When you burn a book, shred a document, or delete a computer file, the information isn't gone, it's redistributed. The precise arrangement of particles that made up those documents is now encoded in the motion and position of countless air molecules, in thermal radiation, in subtle gravitational effects. In principle, with a powerful enough computer and perfect knowledge of the present state of the universe, you could reconstruct those shredded documents exactly. This leads us to a remarkable connection with thermodynamics and entropy. The apparent loss of information we observe in everyday life is really just information becoming more dispersed and harder to access, exactly like heat spreading through a system. The second law of thermodynamics doesn't violate information conservation. It simply describes how information naturally spreads out and becomes practically inaccessible. The implications become even more profound when we consider black holes. Hawking's calculations suggested that black holes eventually evaporate through quantum processes, seemingly destroying the information about everything that fell into them. This apparent violation of information conservation sparked decades of debate in theoretical physics. The resolution, proposed by Susskind and others, suggests that the information must somehow be preserved in the Hawking radiation emitted as the black hole evaporates, though the exact mechanism remains hotly debated. The conservation of information has deep philosophical implications beyond physics. It suggests that the past isn't really gone. It's still encoded in the present state of the universe. Every thought you've ever had, every word you've ever spoken, every action you've ever taken, the information about all of these events still exists somewhere in the universe's vast ledger. This principle also connects to quantum mechanics in fascinating ways. The famous no-cloning theorem proves that it's impossible to create a perfect copy of an unknown quantum state. Doing so would effectively create new information, violating conservation. Similarly, The phenomenon of quantum entanglement can be understood as information being shared between particles in ways that must respect overall conservation. The experimental evidence for information conservation continues to grow. In 2019, researchers at the Moscow Institute of Physics and Technology demonstrated the reversal of quantum time evolution, showing how information preserved in quantum correlations could be recovered. Similar experiments with quantum computers have shown how apparently lost quantum information can be retrieved through careful manipulation of quantum systems. As you watch those classified documents turn to strips in the shredder, you might take comfort or feel disturbed, knowing that the information isn't really gone. It's simply been transformed, scattered into the cosmic ledger that records everything that ever was or will be. The universe, it seems, is the ultimate bookkeeper, never forgetting a single detail of its endless story. Black hole information loss. You've just successfully digitized yourself and transmitted your data stream directly into a black hole, becoming the first human to experience spaghettification firsthand. Except, there's a problem far worse than being stretched into cosmic pasta. According to quantum mechanics, the information that makes you you must be preserved, but Einstein's general relativity suggests it will be irrevocably destroyed. You're now at the center of one of physics' most profound paradoxes, one that has brilliant minds like Stephen Hawking completely reversing their positions. The conflict emerged in the 1970s when Hawking demonstrated that black holes slowly evaporate through what we now call Hawking radiation. While this breakthrough helped unite quantum mechanics with gravity, it created an enormous problem. The radiation appeared to be completely random, meaning that anything falling into a black hole would eventually vanish without a trace when the black hole evaporated, a direct violation of quantum mechanics' most sacred principle. Information cannot be destroyed. To understand why this is so troubling, we need to grasp what physicists mean by information. In quantum mechanics, information isn't just data. It's the complete specification of a system's quantum state. If you know the quantum state of every particle in your body right now, you could theoretically predict every possible future state. This predictability is fundamental to quantum mechanics, which tells us that information must always be preserved, even if it becomes scrambled beyond practical recognition. This preservation principle has been verified countless times in particle physics experiments. When particles collide and transform at nearly light speed, physicists can always trace the quantum information through the chaos. But black holes seem to break this rule completely. As matter falls in, crossing the event horizon, its quantum information appears to vanish when the black hole eventually evaporates, leaving behind only random radiation. The implications are staggering. If information truly disappears in black holes, we'd need to rewrite quantum mechanics from the ground up. This isn't just an abstract concern. Quantum mechanics forms the basis for our understanding of everything, from chemical reactions to the early universe. Its principles underpin technologies from lasers to quantum computers. In 1997, theoretical physicist Leonard Susskind and Gerard T. Hooft proposed a potential solution, the holographic principle. They suggested that information about everything inside a black hole might be encoded on its surface, its event horizon, much like a 3D image encoded on a 2D hologram. This would mean information isn't truly lost, just transformed into a different dimensional representation. But this elegant solution raised new puzzles. If information is preserved at the event horizon, what happens to the quantum state of objects that have already fallen in? We can't have the same information existing in two places. That would violate another fundamental quantum principle called the no-cloning theorem. This became known as the firewall paradox. Either information is lost, or we need some mechanism that destroys incoming information at the event horizon, the firewall, which would violate Einstein's principle that nothing special happens at the event horizon from the perspective of someone falling in. The plot thickened in 2004 when Hawking himself dramatically reversed his position, admitting that information might be preserved after all. His new calculations suggested that quantum fluctuations could allow information to escape, though the mechanism remains unclear. This led to the current prevailing view that information must somehow be preserved, but exactly how remains one of physics' greatest unsolved mysteries. Recent theoretical work has suggested even more exotic possibilities. Some physicists propose that black holes might be creating quantum copies of information in baby universes, or that space-time itself might be composed of quantum bits that preserve information in their fundamental structure. Others suggest that our basic notion of time breaks down near black holes in ways that make our usual concepts of information preservation meaningless. Your digitized self, now approaching the singularity, embodies this fundamental tension in modern physics. Every quantum bit of your consciousness is either about to be irretrievably lost, violating the foundations of quantum mechanics, or preserved in some profound way we don't yet understand. You're not just being stretched into spaghetti, you're testing the very fabric of reality's information structure. As we watch your data stream disappear beyond the event horizon, we're left with a profound question about the nature of information itself. Perhaps, like the cat in Schrödinger's famous thought experiment, the information about your quantum state is both preserved and destroyed until we develop a deeper understanding of how quantum mechanics and gravity truly interact in the extreme environment of a black hole. Neurological time perception. You're sitting in your favorite chair, reading a book, when suddenly the world around you begins to move like molasses. The cat, jumping from the windowsill, hangs suspended in midair. Dust motes drift by with painful slowness, and even the ticking of the clock has stretched into long, languorous beats. Yet your thoughts race at normal speed. You're fully aware, fully conscious, trapped in a bubble where time itself seems to have gone wrong. This isn't science fiction. This exact phenomenon has been documented in cases of extreme trauma and certain neurological conditions, and it opens up one of the most perplexing questions in neuroscience. What exactly is our experience of time, and how does our brain create it? The fascinating reality is that our perception of time isn't like our other senses. We don't have dedicated time receptors the way we have receptors for light or sound. Instead, our brain constructs our experience of time through a complex interplay of neural networks, memory formation, and sensory integration. This was first systematically studied by French physiologist Michel Siffre, who in 1962 spent 2 months living in a cave without any way to track time. His experiments revealed substantial disconnects between perceived time and actual time, sometimes varying by several hours per day. More recent research has revealed that our brain's timing mechanisms operate on multiple levels simultaneously. At the millisecond level, timing is handled by neural circuits in the cerebellum, crucial for physical coordination. The suprachiasmatic nucleus manages our circadian rhythms across 24-hour periods. But our conscious experience of time, the subjective feeling of duration, appears to be processed primarily in the insular cortex and striatum, regions also involved in emotion and memory formation. This brings us to a rather remarkable discovery from a 2013 study at the University of Edinburgh. Our perception of time isn't continuous at all. Instead, our brain processes time in discrete chunks of about 100 milliseconds, something like the frames of a film. These chunks are then seamlessly stitched together to create our impression of flowing time. It's rather like a Victorian zoetrope, creating the illusion of movement from still images. Except we're doing it with moments rather than pictures. The implications of this are properly mind-bending. That smooth, continuous experience of reality you're having right now. It's actually being constructed retrospectively by your brain, roughly 1/10 of a second after things actually happen. You're perpetually living ever so slightly in the past, in a carefully constructed model of reality that your brain has assembled from these discrete temporal chunks. This helps explain those bizarre time distortion experiences. When adrenaline floods your system during moments of extreme stress or danger, your brain processes information more quickly, taking in more detail per discrete chunk of time. When these memories are played back at normal speed, everything seems to have happened in slow motion. It's rather like shooting video at 120 frames per second and playing it back at 30. Everything appears slowed down, but with extraordinary clarity. The rabbit hole goes deeper. Studies of patients with various neurological conditions have shown that our sense of time can be radically altered by changes in brain chemistry. Patients with Parkinson's disease, for instance, often experience time as moving more slowly than it actually does, while those taking dopamine-increasing medications may experience time as moving more quickly. This suggests our experience of time is intimately linked with our brain's dopamine systems, the same networks involved in pleasure, reward, and motivation. Perhaps most intriguing is what this tells us about consciousness itself. If our experience of time is constructed rather than perceived directly, what does this mean for our notion of the present moment? The philosopher Daniel Dennett suggests that consciousness itself might be more like a multiple drafts model, where our brain is constantly creating and revising multiple versions of reality, with our conscious experience being the winning draft that best fits the available data. The implications ripple out into physics as well. Einstein showed us that time itself is relative, varying with velocity and gravitational fields. But these neurological findings suggest something perhaps even more profound, that our subjective experience of time isn't just relative, but actively constructed. We're not passive perceivers of time's flow, but active participants in creating our temporal experience. As you sit there, perhaps still imagining that slow motion scene from earlier, consider that your brain is performing this remarkable feat of temporal construction right now, stitching together discrete moments into the seamless flow of experience. Time, it seems, isn't something that simply passes. It's something our brains are actively creating, moment by discrete moment, in an endless dance of perception and reconstruction that gives rise to our experience of now. Special relativity distortion. You're piloting an experimental spacecraft on humanity's first faster-than-light test flight when your onboard computer displays an alarming message. According to its calculations, you've arrived at Alpha Centauri 3 years before you left Earth. As you sit there, supposedly existing 3 years before your own departure, the true weight of Einstein's special relativity begins to sink in. Time dilation isn't just some mathematical curiosity. It's a fundamental feature of our universe that becomes impossible to ignore at high velocities. When Einstein published his paper on special relativity in 1905, he wasn't just tweaking Newton's laws. He was revealing that space and time themselves are far stranger than anyone had imagined. The core insight came from a deceptively simple observation. The speed of light in a vacuum is always constant, regardless of the observer's motion. This seemingly innocent fact leads to profound consequences. If light always travels at the same speed, then something else must give, and that something is the very fabric of space and time itself. To understand why, let's follow Einstein's thought experiment about traveling alongside a beam of light. If you could somehow catch up to a light beam, classical physics suggested you'd see light frozen in place, like a wave suspended in mid-motion. But this contradicted Maxwell's equations, showing that light always propagates at the same speed. Einstein realized both couldn't be true. Either Maxwell was wrong about light's constant speed, or our basic assumptions about space and time needed radical revision. The mathematics showed that as objects accelerate toward the speed of light, time itself begins to slow down from the perspective of stationary observers. This isn't an illusion or trick of measurement. It's a real effect that's been confirmed countless times through precise atomic clocks. When scientists sent atomic clocks around the world on airplanes in 1971, they found that the flying clocks fell slightly behind their stationary counterparts, exactly as Einstein's equations predicted. But time dilation is just the beginning. Special relativity also reveals that space itself contracts along the direction of motion. An object moving at extremely high speeds would appear compressed to a stationary observer, while the moving object would perceive the rest of the universe as compressed along its direction of travel. This leads to the famous barn pole paradox, where a 20-meter pole, moving at relativistic speeds, could theoretically fit inside a 10-meter barn, at least from certain frames of reference. The implications become even more mind-bending when we consider that these effects aren't just abstract possibilities. They're happening right now, all around us. GPS satellites must constantly correct for relativistic time dilation to maintain accuracy. Without accounting for special relativity, their position calculations would drift by about 10 kilometers per day. These distortions of space and time lead to apparent paradoxes that strain our intuition. The twin paradox describes how a space-traveling twin would return to Earth younger than their Earth-bound sibling. While this seems to violate symmetry, shouldn't each twin see the other as aging more slowly? The acceleration required for the traveling twin to return breaks the symmetry and resolves the paradox, though not without challenging our fundamental understanding of time itself. What's particularly remarkable is how these effects emerge from pure logical necessity once we accept the constant speed of light. There's no special mechanism that causes time to slow down or space to contract. These distortions are simply what must happen for the laws of physics to remain consistent across different reference frames. The implications extend far beyond physics. Special relativity demonstrates that our common sense notions about the nature of reality, absolute time, simultaneous events, rigid space, are merely approximations that work well at everyday speeds. The true structure of our universe is far more fluid and interconnected than we imagined. This brings us back to your hypothetical faster-than-light spacecraft. The reason you've seemingly arrived before you left isn't just a quirk of mathematics. It's a fundamental warning sign that faster-than-light travel would violate causality itself. According to special relativity, any object with mass would require infinite energy to reach the speed of light, let alone exceed it. The universe appears to have a built-in speed limit, and it's not just a practical limitation, but a necessary feature to prevent logical paradoxes from unraveling the fabric of space-time itself. As you sit in your impossible spacecraft, contemplating your equally impossible temporal predicament, you're experiencing firsthand why Einstein's special relativity isn't just another scientific theory. It's a fundamental revelation about the nature of reality itself. The fact that these bizarre distortions of space and time are necessary features of our universe rather than bugs might be the most remarkable aspect of all. Relativistic time dilation. You're sitting in a coffee shop, casually glancing at your watch, 3:15 p.m. on a Tuesday afternoon, when your identical twin walks in, looking noticeably younger than you. She's been away on what she says was a 6-month deep space mission, but according to your family photos and calendar, she's been gone for 4 years. Both of you are absolutely certain about the time that's passed, and oddly enough, you're both completely right. This isn't science fiction. It's a very real consequence of Einstein's special theory of relativity, first published in 1905. The paper, on the electrodynamics of moving bodies, introduced the world to a mind-bending truth. Time isn't absolute. It flows differently depending on how fast you're moving relative to someone else. The mathematics behind this phenomenon emerged from Einstein's struggle with a seemingly simple question. Why does light always appear to travel at exactly the same speed, regardless of how fast the observer is moving? This stubborn consistency of light speed led to an inacceptable conclusion. If light speed never changes, then time itself must change to accommodate it. Let's break this down with your twin's space mission. While she was traveling at extremely high speeds relative to Earth, time literally passed more slowly for her than it did for you. This isn't a trick of perception or a measurement error. It's the actual nature of time itself. The faster an object moves through space, the slower it moves through time. It's as if we all have a cosmic speed limit. We can move quickly through space or quickly through time, but not both simultaneously. The effect becomes noticeable only at very high speeds, which is why we don't experience it in our daily lives. At 10% of the speed of light, the time difference is subtle, but at 99.9% of light speed, the effect becomes dramatic. For every year that passes on Earth, someone moving at that speed would experience only about 16 days. This isn't just theoretical physics. We have proof. In 1971, physicists Joseph Hafele and Richard Keating flew atomic clocks around the world on commercial aircraft. When compared to identical clocks that stayed on Earth, the flying clocks showed a time difference exactly matching Einstein's predictions. Even more remarkably, GPS satellites must account for time dilation in their calculations. Without these corrections, your phone's navigation would be off by miles within a single day. But here's where it gets truly bizarre. From your twin's perspective during her journey, she wasn't the one moving at all. Earth was the object, racing away from her at near light speed. According to her frame of reference, time was passing normally for her, while everyone on Earth was experiencing accelerated time. This is the principle of relativity. There's no universal correct frame of reference. Both perspectives are equally valid. This leads us to the famous twin paradox. How can both twins be right about who is aging more slowly? The resolution lies in the fact that your space-traveling twin had to accelerate away from Earth and then decelerate to return, creating an asymmetry in the situation. She experienced actual forces during acceleration and deceleration, while you remained in an inertial frame of reference on Earth. The implications extend far beyond personal aging. Time dilation affects everything: chemical reactions, biological processes, even the rate at which thoughts form in your brain. If we could somehow observe your twin during her high-speed journey, we would see everything about her moving in slow motion, her heart beating slower, her movements languorous, even her words stretching out over longer periods. This brings us to a profound realization about the nature of reality. Time isn't a fixed backdrop against which events occur. It's a dynamic dimension that warps and bends based on motion and gravity. The clock you're looking at in that coffee shop isn't measuring some universal time flow. It's measuring the local passage of time in your specific frame of reference. When your twin sits down across from you, orders her coffee, and begins to tell you about her 6-month journey, you're witnessing one of nature's most fundamental truths: the malleability of time itself. Your different experiences of time's passage aren't a disagreement to be resolved. They're proof that Einstein's universe is far stranger and more fascinating than our everyday experience suggests. And there you sit, two identical twins of different ages, both absolutely correct about the time that's passed, demonstrating that in our universe, even the most basic assumptions about reality, like the steady, uniform flow of time, turn out to be merely comfortable illusions that break down when we venture beyond our ordinary experience. Hydrostatic equilibrium paradox. You're standing in a submarine at the bottom of the Mariana Trench, watching in horror as the reinforced walls slowly start to buckle under 15,750 pounds per square inch of pressure, enough force to crush a tank like a tin can. Yet somehow, the bizarre creatures swimming past your viewport remain completely intact, their delicate tissues seemingly immune to these crushing depths. Even stranger, the water inside their bodies isn't bursting outward despite being under the exact same immense pressure. This apparent impossibility sits at the heart of one of physics' most elegant paradoxes. This pressure puzzle first caught the attention of 17th century natural philosophers who struggled to explain how deep-sea life could possibly survive such extreme conditions. The mathematical framework for understanding this phenomenon wouldn't emerge until 1738, when Swiss physicist Daniel Bernoulli published his seminal work, Hydrodynamic, which laid the groundwork for our modern understanding of fluid dynamics and pressure equilibrium. The key to unraveling this paradox lies in the nature of hydrostatic pressure itself. Unlike solid materials that can maintain pressure differentials across their surfaces, fluids distribute pressure equally in all directions. This fundamental property, known as Pascal's law, formalized by Blaise Pascal in 1647, means that the pressure inside an organism at depth perfectly matches the crushing pressure outside. But this leads us to an even more perplexing question. If the pressures are equal, why doesn't all that internal pressure tear the creature apart from within? The answer reveals a beautiful symmetry in nature's design. Every molecule of water inside the organism is indeed pushing outward with tremendous force, but it's precisely matched by the external pressure pushing inward. This perfect balance creates what physicists call a state of hydrostatic equilibrium. It's rather like being squeezed equally from all directions. There's nowhere for anything to go, so everything stays exactly where it is. This principle extends far beyond deep-sea creatures. In fact, it's the same mechanism that keeps our own bodies from collapsing under atmospheric pressure at sea level. We're constantly being subjected to 14.7 pounds per square inch of pressure, but we never notice because our internal pressure perfectly matches it. The real challenge for deep-sea life isn't dealing with high pressure itself, but rather managing the transition between different pressure zones. This brings us to a fascinating connection with astrophysics. The same hydrostatic equilibrium that keeps a jellyfish intact at the bottom of the ocean also prevents stars from collapsing under their own gravitational weight. In stars, the outward pressure from nuclear fusion perfectly balances the inward pull of gravity. When this equilibrium fails, we get supernovae, rather more dramatic than a popped fish, but governed by the same fundamental principles. The implications of this paradox extend into modern engineering challenges. Submarines must be built as rigid pressure vessels precisely because they can't achieve true hydrostatic equilibrium like biological organisms. Their internal airspace can't match the pressure of the depths without crushing the human occupants. This limitation has led to fascinating developments in bio-inspired design, where engineers study how deep-sea creatures manage pressure adaptation to create more efficient underwater vehicles. The hydrostatic equilibrium paradox also helps explain one of the ocean's most remarkable features, the existence of distinct layers of water that barely mix, even over centuries. These layers maintain their separation through minute differences in temperature and salinity, creating what oceanographers call thermoclines and haloclines. It's rather like having multiple oceans stacked on top of each other, each maintaining its own perfect balance of pressures. Perhaps the most elegant aspect of this paradox is how it demonstrates nature's efficiency. Evolution has produced creatures that don't need thick armor or complex pressure management systems to survive at depth. They simply work with the physics rather than against it. Their tissues and cells are designed to be incompressible, allowing them to achieve perfect pressure balance without expending any energy at all. As you watch those deep-sea creatures gliding past your submarine window, remember that they're not so much resisting the crushing pressure as they are becoming one with it. In their effortless existence at the bottom of the ocean, they're demonstrating one of physics' most beautiful principles. Sometimes the best way to deal with overwhelming force is to simply let it flow through you, around you, and within you in perfect balance. Quantum measurement collapse. You're standing in a laboratory, your hand hovering over a button that will determine whether a cat in the next room lives or dies. Except that's not quite right, because according to quantum mechanics, until you press that button and look inside, the cat exists in a superposition of both states simultaneously. It's the famous Schrödinger's cat thought experiment. But here's what they don't tell you in the popular accounts. The real mystery isn't about the cat at all. The profound puzzle at the heart of quantum mechanics is what happens in that instant when you finally open the box and look inside. The phenomenon known as quantum measurement collapse sits at the intersection of physics and philosophy, raising questions that have haunted scientists since the early days of quantum theory. In 1927, at the 5th Solvay Conference in Brussels, the greatest minds in physics gathered to wrestle with this exact problem. Niels Bohr and Albert Einstein engaged in historic debates about the nature of reality itself, all centered around what happens when we observe quantum systems. At its core, quantum measurement collapse describes how a quantum system, existing in multiple possible states simultaneously, suddenly collapses into a single definite state when measured. Before measurement, quantum systems exist in what's called a superposition, a mathematical combination of all possible states. The mathematics developed by Paul Dirac and John von Neumann in the 1930s works beautifully. But the physical interpretation of what's actually happening remains deeply mysterious. Take a simple electron. According to quantum mechanics, Before we measure its spin, it genuinely exists in a superposition of spinning both up and down at the same time. This isn't just a limitation of our knowledge, the electron really is in both states. But the moment we measure it, something remarkable happens. The wave function, which describes all these possible states, collapses instantaneously into just one outcome. The implications are staggering. If we accept the standard Copenhagen interpretation, proposed by Bohr and Heisenberg, consciousness itself seems to play a special role in the universe. The act of observation somehow causes physical reality to crystallize from a fog of possibilities into concrete actuality. It's no wonder Einstein was deeply troubled by this, famously asking whether the moon exists when nobody looks at it. But there's an even deeper problem. The mathematics of quantum mechanics tells us nothing about how or why this collapse occurs. The Schrödinger equation, which governs how quantum systems evolve, is entirely deterministic and continuous. Yet measurement seems to introduce a discontinuous, probabilistic element that's simply not present in the underlying mathematics. This has led to numerous alternative interpretations. Hugh Everett III proposed the many worlds interpretation in 1957, suggesting that collapse never actually happens. Instead, every possible outcome occurs in branching parallel universes. Roger Penrose argues that gravity might be responsible for collapse, while others propose that decoherence, the interaction between quantum systems and their environment, might explain the appearance of collapse without requiring it to actually happen. The phenomenon connects to other deep mysteries in physics. The quantum Zeno effect, first proposed by Alan Turing's colleague Emil Post, suggests that constantly measuring a quantum system can freeze it in place, preventing it from evolving. It's as if the act of observation itself can halt the flow of time for quantum particles. This has actually been demonstrated experimentally with trapped atoms, raising profound questions about the nature of time and measurement. Each proposed solution seems to raise as many questions as it answers. If consciousness causes collapse, what exactly counts as consciousness? If parallel universes exist, why do we only experience one outcome? If decoherence is the answer, where exactly does the quantum world end and the classical world begin? The measurement problem has practical implications too. Quantum computers rely on maintaining quantum superpositions, but measurement collapse threatens to destroy the very quantum properties we're trying to harness. Understanding the nature of measurement collapse isn't just philosophy, it's crucial for developing future technologies. What's particularly striking is how this seemingly abstract problem touches on fundamental questions about the nature of reality. Are we discovering the universe's properties through measurement, or are we somehow participating in creating reality through the act of observation? The answer could reshape our entire understanding of consciousness, free will, and the role of the observer in the cosmos. As you stand there in that laboratory, hand still hovering over that button, you're not just participating in a thought experiment, you're confronting one of the deepest mysteries in all of physics, one that suggests the act of observation itself might be more fundamental to reality than we ever imagined. The cat might be both alive and dead, but the real question is what role you play in resolving that uncertainty into concrete reality. Quantum state transfer. You're standing in two places at once, literally. Not metaphorically, not theoretically, but actually existing in two distinct locations simultaneously. Your quantum state, perfectly copied, across space, in complete violation of what should be possible. This isn't science fiction, it's a real phenomenon called quantum state transfer, and it's one of the most profound demonstrations of how reality behaves nothing like our intuitions suggest. The first experimental demonstration of quantum state transfer occurred in 2004 at the University of Innsbruck, when a team led by Dr. Rainer Blatt managed to transfer the quantum state of one calcium ion to another across a microscopic distance. It wasn't just information being copied, it was the complete quantum state, including all its bizarre superpositions and entanglements. To understand why this is so revolutionary, we need to grasp what a quantum state actually is. Unlike classical physics, where objects have definite properties, quantum states exist as probability distributions of multiple possible states simultaneously. It's rather like having a die that's simultaneously showing all 6 numbers until you look at it. Except even that analogy falls short of capturing the true strangeness. The quantum no-cloning theorem, first proposed by William Wouters and Wojciech Zurek in 1982, tells us it's impossible to create an identical copy of an arbitrary quantum state. This isn't just a technical limitation, it's a fundamental law of nature. You can't duplicate quantum information without destroying the original. It would be like trying to copy a book by reading it, except the act of reading makes the original text vanish. But quantum state transfer finds a clever loophole. Instead of copying the state, it moves it, rather like transferring water from one glass to another. The original state is destroyed in the process of being transferred, preserving the no-cloning theorem while still achieving what seems impossible: the perfect transmission of quantum information across space. The applications are staggering. Quantum computers could use state transfer to move quantum bits, qubits between different parts of the processor. Quantum networks could teleport information across vast distances. We might even create quantum repeaters that extend the range of quantum communication by transferring states between intermediate points. But the implications go far deeper than practical applications. Quantum state transfer reveals something profound about the nature of information itself. In classical physics, information is just a description of physical systems, like writing down the position and velocity of a particle. But quantum mechanics suggests information is itself a fundamental physical quantity, as real and substantial as energy or momentum. This leads us to a fascinating philosophical question. What exactly is being transferred during quantum state transfer? It's not matter or energy in any conventional sense. It's pure information, yet it has physical consequences. It's as if the universe treats information as a kind of substance that can flow from place to place while following its own strange rules. The phenomenon also challenges our understanding of locality, the principle that objects can only be influenced by their immediate surroundings. When a quantum state is transferred, the entire state moves instantaneously, regardless of distance. It's not that information travels faster than light, which would violate causality, but rather that quantum states seem to exist in a realm where ordinary spatial relationships don't apply. Modern experiments have pushed the boundaries even further. In 2019, researchers at Yale achieved quantum state transfer between 2 superconducting circuits separated by more than a meter, an enormous distance in quantum terms. They used a technique called remote entanglement, where 2 quantum systems become correlated in such a way that measuring one instantly determines the state of the other. The implications extend into cosmology. If quantum states can be transferred across space, what happens to quantum information when matter falls into a black hole? Stephen Hawking suggested that information might be lost forever, creating a paradox that still puzzles physicists today. Quantum state transfer offers tantalizing hints about how information might be preserved, perhaps through some yet unknown mechanism of quantum gravity. We're only beginning to explore the possibilities. Researchers are developing protocols for transferring quantum states between different types of systems, from atoms to photons, from superconducting circuits to mechanical oscillators. Each success reveals new aspects of how information behaves at the quantum level. So the next time you send a text message or upload a file, remember, somewhere in the quantum realm, nature is performing an even more remarkable feat of information transfer, moving entire quantum states across space while dancing around the fundamental limits of reality itself. Dark matter distribution. You're floating in the void between galaxies, equipped with special goggles that let you see dark matter as a faint purple haze. As you watch, entire galaxies spin before your eyes like cosmic pinwheels, but something's wrong. The outer edges are moving far too fast, as if invisible hands are pulling on stars that should have long ago been flung into space. The purple haze you're seeing through your goggles reveals the answer. These galaxies are wrapped in massive halos of dark matter, extending far beyond their visible borders. But here's what's truly baffling. This mysterious substance isn't distributed how physics says it should be. The story of dark matter distribution begins in 1933, when Swiss astronomer Fritz Zwicky studied the Coma cluster of galaxies. He noticed the galaxies were moving so quickly that their visible mass alone couldn't generate enough gravitational force to hold them together. By applying the virial theorem to his observations, Zwicky calculated that the cluster must contain about 400 times more mass than what could be seen. He called this invisible substance Dunkelmaterie, or dark matter. But it wasn't until Vera Rubin's groundbreaking work in the 1970s that the distribution puzzle became clear. Rubin and her colleague Kent Ford measured the rotation curves of galaxies, graphs showing how fast stars move at different distances from the galactic center. According to Newtonian physics, stars at the outer edges should move more slowly, just as Pluto moves more slowly than Mercury. Instead, they found that outer stars maintained roughly the same speed as those closer to the center, creating what we call flat rotation curves. This observation demanded an explanation, and dark matter provided it. But the distribution pattern creates a fascinating problem. Computer simulations of galaxy formation, like the influential Millennium simulation run at the Max Planck Institute, suggest dark matter should form a cuspy profile, densely concentrated at galactic centers and thinning out towards the edges. What we actually observe is a chord profile, more evenly distributed, with a relatively constant density in the central regions. This discrepancy between theory and observation is known as the cusp core problem, and it's forced physicists to reconsider fundamental assumptions about dark matter's nature. Some propose that dark matter particles might interact with each other more than we thought, causing them to spread out through some unknown mechanism. Others suggest that regular matter's gravitational effects might reshape dark matter distributions over time. The plot thickens when we look at galaxy clusters. Dark matter maps created through gravitational lensing, where mass bends light like a cosmic magnifying glass, reveal enormous structures called cosmic webs. These dark matter filaments connect galaxies and clusters like an invisible skeleton of the universe. The bullet cluster, formed by two colliding galaxy clusters, provides perhaps the most dramatic evidence of dark matter's distinct distribution. As the clusters passed through each other, the regular matter interacted and slowed down, while the dark matter halos sailed right through, creating a clear separation between visible and invisible mass. This distribution pattern raises profound questions about the universe's evolution. The current leading model, lambda CDM, suggests that dark matter's gravitational effects guided the formation of cosmic structure. Dark matter clumped together first, creating gravitational wells that attracted regular matter, eventually forming the galaxies and clusters we see today. But if this model is correct, why doesn't the observed distribution match our simulations? Adding another layer of complexity, recent observations of dwarf galaxies reveal even more distribution puzzles. These small galaxies should be dominated by dark matter, yet many appear to have less than expected. The too big to fail problem notes that the largest dark matter concentrations predicted by simulations don't match the dwarf galaxies we actually observe. The distribution mystery touches on fundamental questions in physics. Are our theories of gravity correct at galactic scales? Could modified gravity theories like MOND, modified Newtonian dynamics, explain these patterns without dark matter? Or does the answer lie in dark matter's particle nature? Perhaps it's not as cold or non-interacting as we assumed. As you float there between the galaxies, watching the purple haze swirl in patterns that defy our best theories, you're witnessing one of physics' most profound mysteries. The way dark matter distributes itself throughout the universe tells us something's missing in our understanding, either about dark matter itself, about gravity, or perhaps about both. In the end, the void between what we observe and what we expect might hold the key to a deeper truth about the cosmos. Holographic universe theory. You're walking through your living room when suddenly every surface, the walls, floor, ceiling, even your own hands, begins to shimmer and pixelate like a digital display. As you reach out to touch the coffee table, your fingers pass straight through it, and you realize with a jolt that everything around you might be nothing more than information projected onto a two-dimensional surface, like the world's most sophisticated computer screen. This isn't science fiction. It's a serious scientific proposition called the holographic principle, and it suggests that our entire three-dimensional universe might actually be encoded on a two-dimensional surface, much like the way a credit card hologram contains a three-dimensional image on a flat piece of plastic. The idea emerged from decades of work trying to reconcile quantum mechanics with gravity, specifically through studying black holes. In 1974, Stephen Hawking made the groundbreaking discovery that black holes emit radiation and eventually evaporate. This created what became known as the black hole information paradox. If black holes eventually disappear, what happens to all the information about the objects that fell into them? According to quantum mechanics, information cannot be destroyed, yet black holes seem to be doing exactly that. This puzzle led theoretical physicist Leonard Susskind and Gerard 't Hooft to propose something radical in the 1990s. They suggested that all the information about objects falling into a black hole might actually be preserved on its event horizon, the boundary surface of the black hole. Like a hologram storing 3D information on a 2D surface, the event horizon could somehow encode everything about what's inside the black hole. But here's where it gets properly strange. Juan Maldacena took this idea further in 1997 with his ADA-CFT correspondence, mathematically demonstrating that certain quantum theories in flat spacetime could precisely describe gravity in a curved space with an extra dimension. In other words, a complete description of a volume of space might be encoded on its boundary, just like information about a black hole might be encoded on its event horizon. This has profound implications for our understanding of reality. If the principle holds true for black holes, might it not apply to our entire universe? Could everything we experience as three-dimensional reality, every object, every action, every moment, actually be encoded on some distant two-dimensional surface at the edge of our cosmos? The mathematics supporting this idea works surprisingly well. In fact, some physicists use it as a practical tool for solving complex problems in quantum mechanics by translating them into simpler gravitational problems in higher dimensions, or vice versa. It's like having two different languages that can describe the same reality, one in 3 dimensions with gravity and one in 2 dimensions without it. But what does this mean for our everyday experience? If we're truly living in a holographic universe, then space itself might not be fundamental, but emergent, like the way temperature emerges from the collective behavior of atoms, or the way consciousness emerges from neural activity. The solid 3-dimensional world we experience might be more like a very sophisticated optical illusion. This connects surprisingly well with other puzzles in modern physics. The holographic principle might help explain quantum entanglement, that spooky action at a distance Einstein found so troubling. If our 3-dimensional reality is actually encoded on a 2-dimensional surface, then two particles that appear far apart to us might be right next to each other in the fundamental description of the universe. The implications extend even further into questions about the nature of reality itself. If our universe is essentially information encoded on a surface, then what we think of as physical laws might actually be more like information processing rules. Space, time, and matter might be more like the output of an incomprehensibly complex computation than fundamental aspects of reality. Some researchers have even suggested that this could explain the apparent randomness we see in quantum mechanics. Just as a computer screen shows discrete pixels when you look close enough, perhaps the seemingly continuous fabric of space-time breaks down at very small scales because it's actually being generated from discrete information on some cosmic boundary. As you look around your room now, perhaps still half expecting things to start shimmering, you might wonder how different this is from Plato's allegory of the cave. The ancient philosophical proposition that what we perceive as reality might be merely shadows on a wall. The holographic principle suggests something similarly profound, that the solid, three-dimensional world we experience might be a projection of information stored on a surface we can never directly observe. Our universe might be less like the room you're sitting in, and more like the most sophisticated hologram ever created, dancing with unimaginable complexity on the boundary of space itself. Inertial frame paradox. There's a 99.9999% chance you're moving at over 2 million kilometers per hour right now, yet you'd bet your life that you're sitting perfectly still. The truly bizarre part, you're right on both counts. And this apparent contradiction holds the key to understanding how our universe actually works. Our planet Earth spins on its axis at roughly 1,600 kilometers per hour. It simultaneously orbits the Sun at 107,000 kilometers per hour. Our entire solar system whirls around the galactic center at about 720,000 kilometers per hour, and our galaxy itself hurtles through space at nearly 2.1 million kilometers per hour relative to the cosmic background radiation. Yet here you are, feeling completely stationary, and according to the deepest laws of physics, you're absolutely correct about that too. This mind-bending reality first came to light in 1632 when Galileo Galilei published his dialogue concerning the two chief world systems. He described an experiment that would revolutionize our understanding of motion. Below the deck of a smoothly sailing ship, there would be no possible way to determine whether you were moving or standing still. Butterflies would flutter in identical paths, water would drip the same way, and a jumping fish in a bowl would leap the same distance regardless of the ship's velocity. This observation shattered the prevailing Aristotelian view that had dominated scientific thought for nearly 2 millennia. The ancient Greeks believed in absolute motion, the idea that there was a true state of rest against which all movement could be measured. Galileo's ship demonstrated something profound. Motion is inherently relative. There is no universal reference point, no cosmic grid that defines absolute movement. Einstein took this principle to its logical extreme in 1905 with his special theory of relativity. If there's no way to detect absolute motion, then the laws of physics must work exactly the same way in all inertial reference frames. Whether they're stationary or moving at constant velocity, the implications were staggering. Not only is motion relative, but time itself dilates and space contracts, depending on your frame of reference. But the real breakthrough came with Einstein's happiest thought about acceleration and gravity. If you're in an elevator accelerating upward, you feel heavier. If it's accelerating downward, you feel lighter. And if the cables snap and you're in free fall, you feel weightless. Einstein realized there's no experiment you could perform inside that falling elevator to distinguish your situation from floating in empty space. This equivalence between acceleration and gravity became the foundation of general relativity. The mathematics describing this is intricate, but its effects touch our daily lives in surprising ways. Every time you use GPS navigation, you're relying on corrections based on both special and general relativity. The satellites must account for time passing slightly differently for them than for us on Earth's surface, due to both their speed and their position in Earth's gravitational field. Without these corrections, your navigation would drift by kilometers within a day. This puzzle extends beyond physics into philosophy. It challenges our most basic assumptions about motion, rest, and the nature of reality itself. We naturally think of ourselves as either moving or stationary, but these concepts are meaningless without a frame of reference. Even more unsettling, there's no such thing as true simultaneity. Events that appear to happen at the same time in one reference frame may occur at different times in another, and neither perspective is more correct. The implications ripple out into our understanding of the entire universe. When we say the galaxy Andromeda is approaching us at 110 kilometers per second, we must ask, relative to what? When we measure the cosmic microwave background radiation showing the echo of the Big Bang, we find our galaxy moving relative to it. But is that the ultimate reference frame? The answer, beautifully and maddeningly, is no. So as you sit there, seemingly motionless, yet hurtling through space in multiple directions at once, you're experiencing one of physics' most profound truths. All motion is relative, and absolute rest is as impossible as absolute motion. In a very real sense, you're both the fastest moving and the most stationary thing in your own personal universe. And that's exactly how our cosmos works, whether we find it intuitive or not. Inflationary universe model. You're falling infinitely, but the space around you is expanding faster than you can fall. Each second, the void beneath stretches 1 trillion times larger, yet you keep plummeting through the endless dark. This peculiar predicament mirrors our universe's earliest moments, a period of expansion so rapid and violent that it defies our basic intuitions about space and time. In 1979, physicist Alan Guth sat at his desk at Cornell, puzzling over several seemingly unrelated problems in cosmology. The universe appeared impossibly uniform. Every direction we looked showed nearly identical conditions, even though those regions could never have communicated with each other given the speed of light. Even more troubling, space appeared mysteriously flat, balanced on a knife edge of precision that seemed too perfect to be coincidence. Late one night, Guth realized these problems might share a solution. What if the early universe underwent a brief period of exponential expansion? This idea, which became known as cosmic inflation, proposed that in the first fraction of a second after the Big Bang, space itself expanded faster than the speed of light. During this fleeting moment, a microscopic patch of space stretched to become larger than our entire observable universe today. This isn't the gentle expansion we observe now. It was expansion on steroids. In just 10 to the negative 32nd seconds, space expanded by a factor of at least 10 to the 78th. To grasp this scale, if you expanded a single atom to the size of our observable universe, you'd still fall dramatically short of inflation's magnitude. The fabric of space itself stretched so violently that quantum fluctuations, tiny ripples in space-time, were frozen into place, becoming the seeds for all cosmic structure we see today. But this solution raised as many questions as it answered. What powered this explosive growth? Guth proposed a peculiar state of matter called a false vacuum, a high-energy configuration that acted like anti-gravity, driving space apart. This false vacuum would have been unstable, eventually decaying into the normal vacuum we experience today, releasing its enormous energy as matter and radiation in the process. The implications stretch far beyond solving cosmological puzzles. If inflation happened once, it likely happened, and continues to happen, many times. As some regions of false vacuum decay, others continue expanding, spawning new universes in an endless process called eternal inflation. Our observable universe might be just one bubble in an infinite sea of universes, each with potentially different physical laws. This model also suggests something profound about the nature of our cosmic origins. The entire observable universe, every galaxy, star, and atom, may have emerged from a patch of space smaller than a proton. The matter that makes up everything we see didn't exist before inflation. It was created from the energy released when the false vacuum decayed. Recent observations have provided compelling evidence for inflation. The cosmic microwave background radiation, the afterglow of the Big Bang, shows exactly the pattern of tiny temperature variations we'd expect from quantum fluctuations stretched by inflation. The distribution of galaxies across space also matches inflation's predictions with remarkable precision. Yet challenges remain. We still don't know what field or particle played the role of the inflaton, the entity driving inflation. Some theorists worry the model might be too successful, potentially predicting an infinite number of universes where anything that can happen does happen. This multiverse concept makes it difficult to make definitive predictions. The inflationary model also raises deep philosophical questions about the nature of infinity and our place in the cosmos. If eternal inflation creates infinite universes, then everything that can happen does happen, not just once, but an infinite number of times. Somewhere in the multiverse, there are infinite copies of you reading these words, each making slightly different choices in slightly different circumstances. We've come full circle to our falling scenario, but now we understand that the expanding space around you represents one of physics' most profound insights. Just as you can't reach the bottom of our thought experiment, we might never be able to fully grasp the true scope of the cosmos. The inflationary universe model doesn't just explain how our universe began. It suggests we're part of something far larger and stranger than we ever imagined. Perhaps most remarkably, this theory emerged not from complex experiments or massive particle accelerators, but from one physicist trying to solve some puzzling problems about the universe's uniformity. It reminds us that sometimes the most revolutionary ideas come not from new observations, but from looking at existing problems in a completely new way. Neutron star density limit. You're standing on a teaspoon of matter that weighs more than Mount Everest, and yet you're about to witness this impossibly dense cosmic spoonful collapse into something even denser. You found yourself at the exact moment a neutron star reaches its critical mass limit, that precise threshold where quantum mechanics and gravity wage their final battle. The ground beneath your feet, if you can call it that, consists entirely of pure neutrons packed so tightly that the entire mass of Manhattan could fit in a sugar cube. But this extraordinary density isn't even the most remarkable part of your current situation. The year is 1939, and a young J. Robert Oppenheimer is working with his student Hartland Snyder at the University of California, Berkeley. They've just published a paper that would change our understanding of stellar death forever. Their calculations showed something that seemed to violate everything we thought we knew about matter. There's a fundamental limit to how massive a neutron star can be before it catastrophically collapses into what we now call a black hole. This limit, later refined by other physicists and now known as the Tolman-Oppenheimer-Volkoff limit, sits at around 2.5 to 3 solar masses. To understand why this limit exists, we need to dive into the quantum mechanics that keep neutron stars from collapsing in the first place. When a massive star dies in a supernova, its core collapses until the pressure becomes so intense that electrons are forced into protons, creating neutrons. This process, called electron degeneracy pressure, stops when the core becomes a sphere of nearly pure neutron matter. At this point, neutron degeneracy pressure takes over. Thanks to the Pauli exclusion principle, a fundamental quantum mechanical rule stating that no two identical fermions can occupy the same quantum state, the neutrons resist further compression. It's rather like trying to squeeze more people onto an already packed underground train, except these passengers follow strict quantum mechanical rules about personal space. But here's where things get truly bizarre. As more mass falls onto our neutron star, increasing its weight, the gravitational force begins to overwhelm even this quantum mechanical resistance. The neutrons, despite their quantum mechanical objections, are forced closer together. At some point, the gravitational pull becomes so strong that not even the Pauli exclusion principle can prevent further collapse. The mathematics behind this process reveals something profound about the nature of space-time itself. Einstein's field equations, when applied to this scenario, show that once the mass exceeds the Tolman-Oppenheimer-Volkoff limit, space-time curvature becomes so extreme that it creates what mathematicians call a singularity, a point where our current physics breaks down completely. What's particularly intriguing is how this limit connects to other fundamental constants in physics. The exact value depends on the equation of state of nuclear matter. Essentially, how neutrons behave under these extreme conditions. This connects the largest structures we can observe to the smallest scales of quantum mechanics, creating a beautiful bridge between the cosmic and the quantum realms. Recent observations have pushed our understanding even further. In 2019, the LIGO and Virgo collaborations detected gravitational waves from what appeared to be a merger involving a 2.6 solar mass object, right at the edge of this theoretical limit. This detection has forced physicists to reconsider our models of neutron star structure and the exact nature of matter at these extreme densities. The implications extend beyond just stellar physics. This fundamental limit tells us something profound about the nature of matter itself. It suggests that there's a maximum density that normal matter can achieve before it must transform into something else entirely. It's as if the universe has built in a cosmic safety valve, preventing matter from being compressed indefinitely. Back on our teaspoon of neutron star matter, you're witnessing the ultimate battle between quantum mechanics and gravity. The neutrons beneath your feet are packed as tightly as the laws of physics will allow. Any more mass added to this system, and you'll witness the creation of a black hole, the point where gravity finally wins its age-old battle with quantum mechanics. This limit represents one of the most remarkable intersections of quantum mechanics, general relativity, and nuclear physics we've ever discovered. It stands as a testament to how the universe enforces its rules, even in the most extreme conditions imaginable. As you stand there, on the brink between normal matter and something else entirely, you're witnessing one of nature's most fundamental boundaries. The point where the familiar physics of matter gives way to the mysterious realm of black holes. Measurement reality problem. Your quantum measurement just made mathematics itself stop working. The numbers on your lab equipment are shifting between infinite and zero, gravity is becoming optional, and somewhere in Geneva, CERN's computers are spontaneously transforming into butterflies. Your colleague bursts into the lab, white-faced and trembling. "The universe," she whispers. "It's starting to unravel." And she's right. By measuring what quantum mechanics says cannot be measured, you've created a paradox that's literally tearing apart the fabric of reality. While this scenario might sound like science fiction, it points to one of physics' most profound and unsettling problems: the fundamental relationship between measurement and reality itself. In 1927, Werner Heisenberg formalized this issue in his uncertainty principle, but the implications run far deeper than simple measurement limitations. The story begins with an apparently simple question. When we measure something, what are we actually doing? In classical physics, measurement seemed straightforward. You're simply observing what's already there. But quantum mechanics revealed something far stranger. The act of measurement itself appears to force reality into a definite state, collapsing what was previously a cloud of probabilities into a single outcome. This isn't just philosophical speculation. The double-slit experiment demonstrates this measurement reality problem in stark terms. When we fire individual particles at a screen with two slits, they create an interference pattern, as if they're waves passing through both slits simultaneously. But if we try to measure which slit each particle goes through, the interference pattern vanishes. The mere act of measurement fundamentally changes what happens. John Wheeler took this even further with his delayed choice experiments. Not only does measurement affect reality, but measurements made after an event seems to have happened can apparently influence how that event occurred in the past. It's as if reality refuses to commit to a definite history until we force it to through measurement. The implications become even more bizarre when we consider quantum entanglement. Einstein famously called it spooky action at a distance, where measuring one particle instantly affects its entangled partner, regardless of the distance between them. The measurement problem here suggests that reality isn't just influenced by our observations. It might not even be local in any conventional sense. Some physicists, like Eugene Wigner, push this to its logical extreme with the infamous Wigner's friend thought experiment. If measurement collapses quantum states into reality, what happens when different observers make conflicting measurements? The paradox suggests that objective reality might not exist independently of observation at all. This leads us to what's known as the quantum Zeno effect, named after the ancient Greek philosopher's paradox about motion. By continuously measuring a quantum system, we can actually prevent it from changing states, rather like the proverbial watched pot that never boils, but on a quantum level. It's as if reality itself freezes under our constant observation. The measurement reality problem extends beyond quantum mechanics. In cosmology, we face the observer problem. The universe appears fine-tuned for life, but this observation can only be made by observers who exist because the universe is fine-tuned. It's a cosmic scale version of the measurement paradox. Modern experiments continue to probe these questions. The quantum eraser experiment seems to suggest that measurements can be unmade, while quantum computers exploit superposition states that exist before measurement collapses them. Each new discovery seems to make the relationship between measurement and reality more rather than less mysterious. Some theorists propose that consciousness itself might play a role in measurement, though this remains highly controversial. Others suggest that each measurement splits reality into multiple branches, creating the many worlds interpretation of quantum mechanics. Still others argue that we need to completely reconceptualize what we mean by measurement and reality. What's clear is that we've come a long way from the simple notion that measurement merely reveals what's already there. The act of measurement appears to be inextricably woven into the fabric of reality itself. When we observe the universe, we're not just passive observers, we're active participants in a cosmic dance between consciousness and reality. Perhaps the true paradox isn't that measurement affects reality, but that we ever expected it wouldn't. After all, we're not outside the universe looking in. We're part of the system we're trying to measure. Like your hypothetical experiment that began to unravel reality, perhaps the real mystery isn't that measurement changes reality, but that reality allows itself to be measured at all. Optical mirror asymmetry. You're standing in front of a mirror, reaching out to touch your reflection, when something extraordinary happens. Your fingertips pass straight through the glass, meeting your reflection's fingers in a perfect alignment that seems to defy reality. But as you attempt to clasp hands with your mirror self, something feels terribly wrong. No matter how you twist or turn your wrist, you cannot make your palms meet. It's as if you're trying to shake hands with someone who's using the opposite hand, creating an impossible mismatch that reveals one of physics' most peculiar phenomena: optical mirror asymmetry. This seemingly simple observation opens up a fascinating window into the fundamental nature of symmetry and reflection. In 1884, Lord Kelvin first formalized this concept while studying the properties of molecules, noting that some objects, when reflected, create images that cannot be superimposed on their originals through any rotation or translation in three-dimensional space. He termed these objects chiral, from the Greek word for hand. Perhaps the most familiar example of this phenomenon. The mathematics behind mirror asymmetry was further developed through the work of Pierre Curie in the 1890s, who connected it to fundamental symmetry principles in physics. His research showed that this wasn't merely a geometric curiosity, but had profound implications for understanding molecular structure and the behavior of light itself. The key to understanding optical mirror asymmetry lies in the concept of handedness or chirality. Take your right hand and hold it up to a mirror. The reflection you see appears to be a left hand. It cannot be rotated in any way to match your actual right hand perfectly. This property extends far beyond simple hand reflections. It manifests in countless natural structures, from the spiral patterns of snail shells to the molecular arrangement of amino acids in living organisms. Most amino acids used by life on Earth are left-handed, a fact that remains one of biology's great mysteries. This chemical handedness, or homochirality, plays a crucial role in how proteins fold and function. If we created a mirror image version of these molecules, they would be perfectly valid chemically, but completely unusable by our biology. It's as if nature chose a particular handedness at life's beginning, and we've been stuck with it ever since. The implications of optical mirror asymmetry extend into quantum mechanics and particle physics. The weak nuclear force, one of the four fundamental forces of nature, actually violates mirror symmetry. A discovery that earned T.D. Lee and C.N. Yang the Nobel Prize in 1957. This means that certain particle interactions behave differently when viewed in a mirror, challenging our intuitive understanding of nature's symmetries. What's particularly intriguing is how this asymmetry manifests in light itself. When light passes through certain materials, its polarization plane can rotate, a phenomenon known as optical activity. This effect occurs because the molecules in these materials are chiral, causing them to interact differently with left and right-handed, circularly polarized light. Louis Pasteur first observed this in 1848 while studying tartaric acid crystals, laying the groundwork for our understanding of molecular chirality. The practical applications of this phenomenon are surprisingly widespread, from the development of new pharmaceuticals, where molecular handedness can mean the difference between a medicine and a poison, to the creation of new materials for optical computing. Mirror asymmetry plays a crucial role in modern technology. Liquid crystal displays in our devices rely on the manipulation of polarized light through chiral molecules. Perhaps most mind-bending is the question of why our universe exhibits this particular handedness at all. In theory, a mirror image universe with opposite chirality would work just as well. All the laws of physics would remain valid, except for that peculiar weak nuclear force. Yet we find ourselves in a universe with specific handedness preferences, from the spiral arms of galaxies to the twist of DNA helices. Returning to your reflection in the mirror, those mismatched hands represent far more than a simple geometric puzzle. They embody a fundamental aspect of nature's architecture, a cosmic preference for certain types of symmetry breaking that shapes everything from the smallest molecules to the largest structures in the universe. And while you may never be able to properly shake hands with your reflection, perhaps there's something rather wonderful about living in a universe that maintains such subtle yet profound asymmetries. String theory dimensions. You're being torn apart into billions of vibrating strings, each dancing through 11 dimensions of space-time, while your consciousness fragments across realities that fold into themselves like an infinite cosmic origami. And according to physics' most ambitious theory, this is actually the deepest nature of your existence. As your consciousness struggles to process these extra-spatial dimensions, you notice something extraordinary. What appeared to be a simple point in space unfolds into an intricate pattern, like a paper flower blooming in directions that shouldn't exist. This isn't a dream or a thought experiment. According to string theory, this is the fundamental nature of our reality at its smallest scales. In 1921, Theodore Kaluza proposed a revolutionary idea. Our universe might have a hidden fifth dimension. He showed that by adding just one extra spatial dimension to Einstein's equations of general relativity, he could unify gravity with electromagnetism. Swedish physicist Oskar Klein later refined this concept, suggesting this extra dimension might be curled up so tightly we can't detect it, about 10 to the power of negative 35 meters in size. This became known as Kaluza-Klein theory, and while it ultimately failed as a unified theory, it planted the seeds for something far more extraordinary. Fast forward to the 1970s, when physicists realized that the mathematics describing subatomic particles worked better if we assumed these particles weren't actually points, but tiny, vibrating strings. The breakthrough came with a rather awkward discovery. These equations only made sense if space had not just 4 dimensions, 3 spatial plus time, but 10 dimensions. Later versions of string theory would push this even further, suggesting our universe might actually have 11 dimensions. Now, you might reasonably ask why we can't see or feel these extra dimensions. The answer lies in what we call compactification. These additional dimensions are rolled up so incredibly tight that they're effectively invisible to us. Think of an ant walking along a tightrope. To the ant, the rope appears to have 2 dimensions, length and width. From far away, we see only the length. The width becomes negligible. The extra dimensions in string theory are similar, except they're curled up at the Planck scale, roughly 10 to the negative 35th meters. So small that no current technology could ever detect them directly. But these hidden dimensions aren't just mathematical curiosities. They're essential to explaining how different fundamental forces might actually be manifestations of the same underlying phenomenon. The various ways these dimensions can fold and wrap around each other, called Calabi-Yau manifolds, might explain why we observe different types of particles and forces in our visible universe. This leads us to a rather striking implication. What we perceive as particles, electrons, quarks, photons, might actually be different vibrational patterns of these fundamental strings, much like different notes played on a violin string. The key difference is that these cosmic strings vibrate in multiple dimensions we can't perceive, creating the rich symphony of particles that make up our reality. The mathematical beauty of string theory extends even further. In 1995, Edward Witten showed that what seemed to be 5 different string theories were actually different aspects of a single, more fundamental theory called M theory. This unification required the addition of that 11th dimension, making our universe even stranger than previously thought. Perhaps the most profound implication is what string theory suggests about the nature of space itself. At the smallest scales, space isn't smooth and continuous as we perceive it. It's a churning quantum foam where additional dimensions fold and unfold in complex patterns. What we experience as gravity might be the result of how these extra dimensions are warped and curved. The human mind, evolved to navigate 3 spatial dimensions, struggles to truly visualize these concepts. We can describe them mathematically, but our intuition fails us when trying to picture a 7-dimensional sphere or a 6-dimensional Calabi-Yau manifold. It's rather like trying to explain color to someone who's never seen it. We can describe its properties, but the direct experience remains elusive. Coming back to our initial fall through dimensional space, we might view our universe as an intricate origami creation, folded in ways we can't directly perceive. The simplest point in space, when viewed through the lens of string theory, reveals itself to be a complex dance of vibrating strings, echoing through dimensions beyond our everyday experience. While we may never directly observe these extra dimensions, their mathematical necessity in explaining the fundamental nature of reality presents us with a humbling reminder. The universe is not only stranger than we imagine, it's stranger than we can imagine. Wave particle measurement. You're standing in a laboratory, about to perform the most significant experiment in scientific history, except there's a catch. The moment you try to measure whether the quantum object in front of you is a wave or a particle, reality itself seems to shift, transforming the very nature of what you're observing. What's even more maddening is that both states are simultaneously true until you look, at which point one possibility collapses into certainty. Welcome to the bizarre world of wave-particle duality and the measurement problem, where the act of observation fundamentally changes reality. This perplexing phenomenon first emerged in 1927 when Werner Heisenberg proposed his uncertainty principle, but its roots trace back to Thomas Young's double-slit experiment in 1801. Young showed that light passing through 2 parallel slits created an interference pattern on the screen behind, clear evidence that light behaved as a wave. Yet Einstein's 1905 paper on the photoelectric effect demonstrated that light also acted as discrete particles called photons. The scientific community found itself in quite the pickle. How could something be both a wave and a particle? The Copenhagen Interpretation, developed primarily by Niels Bohr and Werner Heisenberg, suggested something remarkable. Quantum objects exist in a superposition of states until measured. It's rather like having a coin spinning on its edge. While spinning, it's neither heads nor tails, but rather both possibilities exist simultaneously. The moment you stop it to look, it becomes one or the other. But this raises profound questions about measurement itself. When exactly does the measurement occur? Is it when the photon hits the detector, when the detector's electronics process the signal, when that information reaches a computer, or when a conscious observer reads the results? This is known as the measurement problem, and it's far more than just a practical consideration. It strikes at the heart of our understanding of reality itself. The implications become even more extraordinary when we consider the delayed choice quantum eraser experiment, first proposed by Wheeler in 1978 and implemented by Kim et al. In 1999. In this devilishly clever setup, the measurement that determines whether a particle behaved as a wave or particle can be made after the particle has already taken its path. It's rather like deciding whether someone took the bus or train to work after they've already arrived at the office, and having that decision retroactively determine which mode of transport they actually used. The mathematics behind quantum mechanics works perfectly. We can predict exactly the probability distributions of various measurements. But when we try to construct a picture of what's actually happening between measurements, we run into philosophical quicksand. Does the wave function represent reality itself, or merely our knowledge of reality? Does consciousness play a special role in collapsing quantum states, as Eugene Wigner suggested? Or are there countless parallel universes where every possible measurement outcome occurs, as Hugh Everett III proposed in his Many Worlds interpretation? These questions have practical implications beyond pure physics. Quantum computers rely on maintaining particles in superposition states, making the measurement problem directly relevant to technological advancement. The development of quantum cryptography similarly depends on our understanding of measurement and observation in quantum systems. What's particularly striking is how measurement in quantum mechanics differs from our classical intuitions. In our everyday world, measuring something doesn't fundamentally alter its nature. When you measure the length of a table, you don't change whether it's made of wood or metal. But in the quantum realm, the very act of measurement determines fundamental properties of what's being measured. This leads us to a rather uncomfortable conclusion. Perhaps objective reality, independent of observation, doesn't exist in quite the way we thought. The act of measurement doesn't just reveal reality, it participates in creating it. It's rather like opening Schrödinger's box, not to find whether the cat is alive or dead, but to participate in determining its fate. The wave-particle measurement problem reminds us that even after a century of quantum mechanics, reality remains far stranger than our classical intuitions suggest. Each answer seems to spawn new questions. Each solution reveals new mysteries. Perhaps that's the true lesson. Not that our measurements are imperfect, but that the act of measurement itself is fundamental to the nature of reality. As you stand in that laboratory, preparing to make your measurement, remember that you're not just observing reality, you're participating in its creation. The quantum object in front of you isn't hiding its true nature. Its true nature includes the very interaction by which you attempt to know it. And there's something rather beautiful about that, even if it does make one's head spin rather more than is strictly comfortable. Gravitational light refraction. You're walking along a quiet street at night when you notice something peculiar. The streetlights above seem to bend and twist, their beams curving through the air like ribbons in the wind. At first, you assume it must be heat distortion, or perhaps your tired eyes playing tricks. But as you look closer, you realize the light itself is being pulled downward, as if caught in an invisible whirlpool. You've just stumbled into one of physics' most remarkable phenomena: light bending under the influence of gravity. This phenomenon, first predicted by Einstein's general theory of relativity in 1915, completely upended our understanding of both light and gravity. The classical Newtonian view held that light traveled in perfectly straight lines, immune to gravitational effects. After all, light has no mass, so how could gravity affect it? But Einstein's revolutionary insight revealed that gravity isn't really a force at all. It's the curvature of space-time itself. The first experimental confirmation came during the solar eclipse of 1919, when British astronomer Arthur Eddington led an expedition to observe stars near the edge of the eclipsed sun. His measurements showed that starlight passing close to the sun's edge was deflected by precisely the amount Einstein had predicted: 1.75 arcseconds. This discovery made front-page news worldwide and transformed Einstein into a global celebrity overnight. But the implications run far deeper than just light bending around stars. The same principle gives rise to gravitational lensing, where massive objects like galaxies act as cosmic magnifying glasses. When light from distant galaxies passes through or around these massive objects, it can be focused, distorted, and even split into multiple images. In 1979, astronomers discovered the first gravitational lens, the twin quasar QSO 0957 plus 561. What appeared to be two nearly identical quasars was actually a single distant object whose light was being split and doubled by a massive galaxy lying between us and the source. This cosmic sleight of hand has become one of astronomy's most powerful tools. By studying how light bends around massive objects, we can measure their mass, detect invisible dark matter, and even spot planets orbiting distant stars. It's rather like deducing the shape of an invisible stone by watching how ripples bend around it in a pond. The mathematics behind gravitational light bending reveals something even more profound about the nature of space and time. Einstein showed that mass warps the fabric of space-time like a heavy ball placed on a rubber sheet. Light follows the shortest possible path through this curved geometry, what mathematicians call a geodesic. So while light always takes the straightest possible path, that path itself can be curved by the presence of mass. This leads to some rather extraordinary possibilities. If space-time is curved enough, say around a black hole, light can actually orbit in a circle, trapped in what's called a photon sphere. At one point, 5 times the Schwarzschild radius of a black hole, the point of no return. Photons can theoretically circle forever, assuming they're placed in exactly the right orbit. It's rather like trying to roll a marble around the rim of a bowl. Get the speed and angle just right, and it could circle indefinitely. The implications extend beyond astronomy into philosophy. If light, the fastest thing in the universe, can be bent and trapped by gravity, what does that tell us about the nature of space and time themselves? The fact that nothing can escape a black hole's gravitational pull, not even light, suggests that space and time themselves break down at the singularity within. Modern applications of gravitational light bending continue to yield surprises. In 2019, astronomers captured the first image of a black hole's shadow using the Event Horizon Telescope, made possible by understanding exactly how light bends in extreme gravitational fields. The image showed a dark circle surrounded by a ring of light, exactly as Einstein's equations predicted over a century ago. The next time you look up at the stars, remember that the light reaching your eyes hasn't traveled in straight lines to get here. It's been nudged and curved by every mass it's passed, carrying within its bent path the signature of gravity's influence. That seemingly simple fact, that gravity can bend light, opened the door to understanding the deepest structure of space and time themselves, and continues to reveal new wonders about our universe. And those streetlights you saw bending, while Earth's gravity is far too weak to create noticeable bending in everyday situations, the principle remains the same, whether we're looking at light passing near a black hole or a street lamp on a quiet night. The universe follows the same rules at every scale. It's just a matter. Second law, heat violation. The laws of physics shatter before your eyes as your morning coffee explodes upward from its mug, freezing mid-air into crystalline spikes while your ceramic cup burns white hot enough to melt steel. You've just witnessed something that physics says should be impossible, a spontaneous violation of the second law of thermodynamics. This apparent paradox strikes at the heart of one of physics' most fundamental principles. The second law of thermodynamics states that the total entropy, essentially the measure of disorder in a system, must always increase over time. Heat flows from hot to cold, never the reverse. Yet in 1876, physicist James Clerk Maxwell proposed a thought experiment that seemed to challenge this universal law, introducing what Lord Kelvin would later dub Maxwell's demon. Maxwell envisioned a tiny intelligent being controlling a small door between two chambers filled with gas. By selectively allowing fast-moving molecules to pass in one direction and slow-moving molecules in the other, this demon could theoretically decrease entropy without expending energy, a clear violation of the second law. The demon would gradually sort the molecules, creating a temperature difference from an initially uniform system. The implications were staggering. If such a demon could exist, it would effectively create a perpetual motion machine of the second kind. You could power entire cities with temperature differences generated from ambient air. Your morning coffee would never grow cold. In fact, it might spontaneously heat itself up while cooling your kitchen. The universe's arrow of time, intrinsically linked to entropy's increase, would lose its direction. But reality isn't so easily fooled. In 1929, Leo Szilard made a crucial observation. The demon itself must gather information about the molecules to sort them. This information gathering and storage requires energy and generates entropy. The demon's brain, or any physical mechanism performing its function, would produce at least as much entropy as it eliminates through sorting. Modern quantum information theory has further illuminated this connection between information and entropy. Work by Rolf Landauer in the 1960s proved that erasing information necessarily generates heat, establishing what we now call Landauer's principle. Every bit of information erased produces at least kT-ln2 energy as heat, where K is Boltzmann's constant and T is temperature. It's rather like trying to balance your checkbook using disappearing ink. The very act of clearing your records costs you something. The demon must eventually clear its memory to continue sorting. And this erasure ensures the second law remains unviolated. Think of it as trying to clean a house where every sweep of the broom creates new dust. The demon can temporarily create local decreases in entropy, but the cost of maintaining its own memory banks ensures the universe's total entropy still increases. This leads us to a profound connection between information and physics. Information isn't just abstract, it's physical. Every bit must be stored in some physical system, whether it's magnetic domains on a hard drive, neurons in a brain, or the quantum states of particles. And manipulating this information always comes with an energy cost. The implications extend far beyond floating coffee. This fundamental link between information and entropy influences everything from the efficiency limits of computers to the physics of black holes. When Stephen Hawking discovered that black holes must emit radiation, he was partly solving a puzzle about what happens to information that falls into a black hole, a problem that continues to vex physicists today. You might wonder, if entropy must always increase, doesn't this mean the universe is heading toward an inevitable heat death, where everything reaches uniform temperature? This troubling question sparked the development of statistical mechanics and our modern understanding of irreversibility. While the laws of physics work equally well forward and backward in time, the overwhelming statistical likelihood of increasing entropy gives time its apparent direction. As you watch your frozen coffee slowly melt back into your now cooling mug, you're witnessing more than just the restoration of thermodynamic order. You're observing the preservation of one of physics' most profound principles. The arrow of time remains unbroken, information stays firmly bound to energy and entropy, and the universe continues its relentless march toward greater disorder, one coffee cup at a time. Molecular memory structure. You've just discovered that every molecule in your body holds a perfect memory of its entire history. Every interaction, every quantum state, every position it has ever occupied since the beginning of time. As you look down at your hands, you realize you're not just seeing skin cells and proteins, but rather an incomprehensibly vast library of information stretching back to the Big Bang itself. The atoms in your left thumb alone contain more historical data than all the world's computers combined. The question is, why can't we access this information? This peculiar reality emerges from one of quantum mechanics' most profound, yet rarely discussed principles, the unitarity of quantum evolution. In 1932, John von Neumann formalized this concept in his groundbreaking work, Mathematical Foundations of Quantum Mechanics, demonstrating that quantum systems preserve information perfectly through time, unlike classical systems, which can lose information through various dissipative processes. Quantum systems maintain a complete record of their past states encoded in their present configuration. The mathematics behind this are remarkably elegant. The Schrödinger equation, which governs quantum evolution, is time reversible. This means that for any given quantum state, you could theoretically run the equation backwards and reconstruct every previous state with perfect accuracy. Each particle's wave function contains, in principle, its entire history, rather like a cosmic version of DNA, but infinitely more detailed. But here's where things get properly mind-bending. This molecular memory isn't just theoretical. In 2019, researchers at the Moscow Institute of Physics and Technology demonstrated that even simple molecules retain quantum information about past interactions in their nuclear spin states. They showed how these molecular memories could persist for surprisingly long periods, though accessing them proved incredibly challenging. The implications of this molecular memory structure extend far beyond pure physics. Take your morning cup of tea, for instance. Those water molecules sloshing about. They're carrying information about their journey from ancient oceans, through clouds, through countless cycles of evaporation and precipitation. The sugar molecules you've added. They contain information about their synthesis in plant cells, about the sunlight that powered their creation, about every bump and jostle since they were packaged. This leads us to what physicists call the quantum measurement problem. While these molecular memories exist in principle, the act of trying to read them fundamentally alters them. It's rather like trying to read a book where opening the pages automatically reorganizes all the words. The very act of measurement forces the quantum system to collapse into a specific state, erasing much of the historical information we're trying to access. The philosophical implications become even more intriguing when we consider consciousness and memory. Your brain's molecules aren't just storing your memories through conventional biochemical mechanisms. They're also maintaining quantum-level records of their entire evolutionary history. There's a kind of double bookkeeping happening: the biological memory we can access, and this deeper quantum memory we can't. This connects rather surprisingly to Roger Penrose's controversial theories about consciousness and quantum mechanics. In his 1989 book, The Emperor's New Mind, Penrose suggested that consciousness might emerge from quantum processes in brain microtubules. While many physicists remain skeptical of this specific idea, the existence of molecular memory adds an interesting dimension to the discussion. Your conscious memories might be just the tip of an unfathomably deep iceberg of information stored in your body's quantum states. The practical applications of molecular memory structure are starting to emerge in quantum computing. In 2021, researchers at IBM demonstrated how molecular quantum memories could be used to create more stable qubits, potentially advancing us toward practical quantum computers. The very property that makes these memories so difficult to access, their quantum nature, makes them perfect for quantum information processing. Perhaps the most profound aspect of molecular memory structure is what it tells us about the nature of information itself. Every particle in the universe carries with it a complete record of its past. Information, in this sense, isn't something we create or destroy. It's fundamental to the fabric of reality itself. Your body isn't just matter. It's a vast archive of cosmic history, written in a language we're only beginning to understand. As you continue your day, consider that every breath you take involves molecules exchanging not just energy, but information. Ancient records passing between your body and the environment in an endless dance of quantum memory. We may never be able to read these molecular memories directly, but understanding their existence fundamentally changes how we think about the relationship between matter, information, and time itself. Universal dark flow. You're drifting through the cosmos in your research vessel when your instruments detect something peculiar. Every galaxy cluster around you is moving in the same direction, as if being pulled by an invisible cosmic hand reaching from beyond the observable universe. Your carefully calibrated equipment confirms it. You've stumbled upon what astronomers call dark flow, one of the most baffling discoveries in modern cosmology that suggests our entire observable universe might be like a leaf caught in an unfathomable current. Back in 2008, a team led by Alexander Kashlinsky at NASA's Goddard Space Flight Center made this startling observation while studying the cosmic microwave background radiation, the afterglow of the Big Bang. Using the WMAP satellite data, they noticed that clusters of galaxies were streaming toward a specific point in the sky at speeds of up to 1,000 kilometers per second. This coherent motion, spanning billions of light years, simply shouldn't exist according to our standard models of cosmology. To understand why this discovery is so revolutionary, we need to step back and look at how we expect the universe to behave. After the Big Bang, matter should have spread out more or less evenly in all directions. While gravity would cause local clumping and clustering, there shouldn't be any large-scale, coordinated movement of galaxy clusters across vast distances. It's rather like throwing confetti in a room. While air currents might cause local swirls and eddies, you wouldn't expect all the pieces to drift uniformly toward the kitchen. The implications of dark flow are staggering. One possibility is that massive structures exist outside our observable universe, their gravitational pull so strong that they influence everything we can see. These hypothetical structures would have formed in the earliest moments after the Big Bang, during a period of rapid expansion called cosmic inflation. It's as if we've discovered that our entire cosmic neighborhood is being tugged by a gravitational anchor we can never directly observe. But here's where things get properly mind-bending. Our observable universe, everything we can possibly see or detect, is limited by the cosmic horizon, roughly 46 billion light-years in any direction. This boundary exists because light from anything further away hasn't had time to reach us since the Big Bang. Dark flow suggests that what lies beyond this horizon isn't just more of the same, but potentially structures so massive they defy our current understanding of physics. Some cosmologists have proposed that dark flow might be evidence of other universes, cosmic neighbors in a vast multiverse. Just as the moon's gravity affects Earth's oceans, despite being outside our immediate environment, these other universes might be exerting a gravitational influence on our own. It's a proposition that transforms our universe from an isolated bubble of space-time into one small part of a much grander cosmic architecture. However, dark flow remains controversial. Subsequent studies using data from the Planck satellite have failed to confirm the original observations, leading some scientists to suggest that the detected motion might be a statistical artifact or the result of systematic errors in the analysis. Yet the original team stands by their findings, and the debate continues in the halls of observatories and research institutions around the world. The controversy itself highlights something fascinating about modern cosmology. We're pushing the very limits of what we can observe and measure. When you're trying to track the movement of galaxy clusters across billions of light years using subtle variations in microwave radiation, you're operating at the razor's edge of our observational capabilities. This uncertainty, rather than diminishing the significance of dark flow, makes it all the more intriguing. It represents one of those rare moments in science where we might be glimpsing something fundamentally new about the nature of our cosmos. Whether dark flow turns out to be real or not, its investigation has already pushed us to consider possibilities we might never have contemplated otherwise. And so we find ourselves in a rather remarkable position. Either we've discovered evidence that our observable universe is being influenced by structures beyond our cosmic horizon, a finding that would revolutionize our understanding of the cosmos, or we've reached the limits of our current observational capabilities, showing us just how challenging it is to probe the largest scales of existence. Your research vessel continues its drift through space, instruments still recording that mysterious universal motion. Perhaps somewhere, beyond the cosmic horizon, lie answers that would transform our understanding of reality itself. But for now, dark flow remains one of those delicious mysteries that remind us just how much we have yet to learn about our cosmic home. Zero-point energy field. You're trapped in the coldest place in the universe, absolute zero. Yet somehow, you're surrounded by an endless dance of particles popping in and out of existence, defying everything we thought we knew about the fundamental nature of nothingness. This isn't science fiction. It's the bizarre reality of the quantum vacuum, and it's happening everywhere, all the time, even as you listen to these words. The discovery of zero-point energy ranks among physics' most startling revelations. In 1913, while working on quantum theory, Albert Einstein and Otto Stern first recognized that quantum systems must retain some residual energy even at absolute zero. This seemingly impossible observation flew in the face of classical physics, which insisted that all molecular motion should cease at the lowest possible temperature. But the quantum world rarely plays by our intuitive rules. By the late 1920s, Werner Heisenberg's uncertainty principle had provided the theoretical framework to explain this peculiar phenomenon. According to quantum mechanics, it's impossible to know both the position and momentum of a particle with perfect precision. There's always some fundamental uncertainty. This uncertainty principle, combined with the wave-particle duality of quantum mechanics, leads to an inescapable conclusion. True emptiness is impossible. Even in what we'd classically consider perfect vacuum, quantum fields fluctuate constantly. These fluctuations give rise to virtual particles that appear and disappear in vanishingly small amounts of time, borrowing energy from the vacuum itself. It's rather like having a cosmic overdraft facility. Particles can temporarily borrow energy from nothing, as long as they pay it back quickly enough that the universe doesn't notice the debt. The experimental confirmation of zero-point energy came through several remarkable observations. In 1948, Dutch physicists Hendrik Casimir and Dirk Polder predicted that two parallel metal plates placed in a vacuum would be pushed together by these quantum fluctuations. This Casimir effect was finally measured with high precision in 1997 by Steve Lamoro at Los Alamos National Laboratory, proving beyond doubt that the vacuum is anything but empty. But the implications of zero-point energy stretch far beyond mere theoretical curiosity. These quantum fluctuations affect everything from the stability of atoms to the very expansion of the universe. When physicists calculate the energy density of the quantum vacuum, they arrive at numbers so enormous they border on the absurd, suggesting there's enough energy in the space of a single coffee cup to boil all Earth's oceans. This leads us to one of physics' most embarrassing problems, the cosmological constant problem. Einstein's theory of general relativity predicts that the energy of empty space should cause the universe to either rapidly expand or collapse. Yet when we look at the actual expansion of the universe, we find it's proceeding at a much gentler pace than quantum mechanics would suggest. The difference between theoretical predictions and astronomical observations is off by a factor of 10 to the 120th power, possibly the largest discrepancy between theory and experiment in the history of science. The plot thickens when we consider the role of zero-point energy in quantum computing. These quantum fluctuations create what we call quantum noise, which can interfere with the delicate quantum states needed for quantum computation. Yet, ironically, some researchers are exploring ways to harness these same fluctuations to power quantum devices or create more secure encryption methods. What's particularly mind-bending is how zero-point energy challenges our very concept of nothing. We tend to think of empty space as a blank canvas on which the universe paints its particles and forces. But quantum mechanics reveals space itself as an active, roiling medium, more like a turbulent ocean than an empty stage. Even removing every particle, every photon of light, and cooling a system to absolute zero wouldn't eliminate this fundamental cosmic jitter. The existence of zero-point energy raises profound philosophical questions about the nature of reality itself. If true nothingness is impossible, what does that mean for our understanding of existence? Perhaps the ancient Greek philosopher Parmenides was right when he argued that nothing cannot exist, though surely not for the quantum mechanical reasons we now understand. As you sit there, seemingly still, you're actually surrounded by an invisible sea of quantum fluctuations, with virtual particles popping in and out of existence, trillions of times each second. It's a reminder that even in apparent emptiness, the universe harbors deep and fundamental mysteries, and that sometimes nothing can be quite something after all. Einstein's elevator principle. You're plummeting down an elevator shaft in a top-secret research facility, watching your coffee cup float serenely beside you as both you and it fall at precisely 9.8 meters per second squared. In this terrifying yet oddly peaceful moment, you've stumbled upon one of physics' most profound insights, the principle that helped Einstein revolutionize our understanding of gravity and space-time. This deceptively simple observation, that objects in free fall appear weightless to each other, became the cornerstone of Einstein's breakthrough in developing general relativity. In 1907, while working as a patent clerk in Bern, Switzerland, Einstein called this realization the happiest thought of my life. The idea that gravity and acceleration were somehow equivalent unlocked a puzzle that had confounded physicists since Newton's time. The principle, formerly known as the equivalence principle, states that there's no experiment you could perform in a closed elevator to distinguish between being in a gravitational field or accelerating through space. If you're in an elevator accelerating upward at 9.8 meters per second squared, the force you feel pushing you down is indistinguishable from Earth's gravity. Conversely, in free fall, you experience weightlessness identical to floating in deep space. But the implications run far deeper than floating coffee cups. Einstein realized this equivalence meant gravity wasn't a force at all. Rather, it was a consequence of the curvature of space-time itself. Just as a heavy ball creates a depression in a rubber sheet, massive objects like stars and planets warp the fabric of space-time around them. Other objects aren't so much pulled by gravity as they are following the natural paths through this curved geometric structure. The experimental evidence supporting this radical idea emerged in 1919, when Sir Arthur Eddington observed light from distant stars bending around the sun during a solar eclipse. Light itself, Einstein predicted, would follow these curved paths through space-time. The observations matched his calculations precisely, instantly making Einstein a global celebrity and confirming that our understanding of gravity needed a complete overhaul. The elevator principle reveals something profound about the nature of reality itself. The laws of physics appear identical whether you're floating in deep space or plummeting toward Earth. This local equivalence suggests a deep unity in how the universe operates, regardless of your frame of reference. It's a principle that continues to be tested with ever-increasing precision, including experiments using ultra-precise atomic clocks that can detect minute variations in the flow of time itself. Modern tests have verified Einstein's predictions to astonishing accuracy. The Gravity Probe B satellite, launched in 2004, used supercooled gyroscopes to measure how Earth's mass warps space-time. The results matched Einstein's calculations to within 1%, confirming that space-time really does curve and twist exactly as general relativity predicts. These ideas extend beyond pure physics into philosophical territory. The principle suggests that our everyday experience of gravity as a force is something of an illusion. We're actually in constant freefall through curved space-time, following geodesics determined by the distribution of mass and energy around us. This represents a fundamental shift in how we understand our relationship with space and time themselves. The implications continue to ripple through modern physics. The detection of gravitational waves by LIGO in 2015 provided yet another confirmation of Einstein's insights, showing how massive accelerating objects create ripples in space-time itself. These waves, predicted by general relativity, took a century to detect, requiring instruments sensitive enough to measure distances smaller than the width of an atomic nucleus, which brings us back to our falling elevator. That peaceful moment of weightlessness reveals something extraordinary. That gravity, the force we experience every moment of our lives, isn't really a force at all. It's the geometry of space-time itself, shaped by mass and energy, guiding everything from coffee cups to light beams along their natural paths through the cosmos. Einstein's happiest thought transformed our understanding of the universe. showing how the seemingly mundane experience of falling could unlock the deepest secrets of space, time, and gravity itself. As your elevator continues its descent, that floating coffee cup demonstrates one of physics' most elegant principles, that the laws of nature reveal themselves in both the grandest cosmic events and the simplest everyday experiences, if only we know how to look. Thermal transport barriers. You're racing through a quantum computer at 3 trillion vibrations per second when suddenly, against every law of thermodynamics, you slam into an invisible force field that threatens to melt the billion-dollar processor beneath you. Welcome to physics' most expensive traffic jam, where heat refuses to flow and the fate of modern computing hangs in the balance. This counterintuitive phenomenon first caught the attention of physicists in the 1950s when they observed something peculiar at the interface between different materials. Heat wasn't flowing as expected. It was getting stuck, creating temperature jumps at boundaries that shouldn't exist according to classical thermodynamics. The effect, now known as Kapitsa resistance, named after Piotr Kapitsa, who first observed it between copper and liquid helium in 1941, threw a wrench into our understanding of heat transfer. The mathematics told us that heat should flow smoothly across interfaces. After all, temperature differences create a thermal gradient, and nature abhors gradients. Yet here was clear evidence that heat transport could be dramatically impeded by nothing more than the meeting point between two materials. It was as if we'd discovered that water refused to flow through certain pipes, despite having clear passage and a downhill slope. The mystery deepened when researchers started examining these barriers at the nanoscale. In 1989, David Cahill and his team at the University of Illinois began systematic studies of thermal boundary resistance across various material interfaces. What they found was startling. The resistance wasn't just a quirk of exotic materials or extreme conditions. It was everywhere, affecting everything from computer chip cooling to heat shield design. The root of this paradox lies in the quantum nature of heat transport. Heat isn't just energy flowing like a fluid, it's carried by quantized vibrations called phonons. These phonons have specific frequencies and wavelengths, much like musical notes. When they encounter an interface between materials, they face a fundamental problem. The atomic structure and vibrational properties of the two materials don't match. It's like trying to transfer the rhythm of a waltz to a jazz ensemble. The beats just don't line up. This mismatch creates what physicists call an acoustic impedance mismatch. Phonons approaching the boundary face 3 possible fates. They can transmit through, though often with changed frequencies, reflect back, or convert their energy into other forms. The process is further complicated by the fact that different phonon frequencies experience different levels of resistance, creating a sort of quantum traffic jam at the interface. But the implications stretch far beyond mere academic curiosity. This seemingly abstract phenomenon has profound consequences for modern technology. The thermal boundary resistance becomes a critical limiting factor in the efficiency of electronic devices. As we push towards smaller and more powerful computers, the heat generated must cross numerous interfaces between different materials. Each boundary acts as a tiny thermal barrier, contributing to the overall heating problem that plagues modern electronics. The paradox has sparked innovative solutions in materials science. Researchers have developed techniques to engineer interfaces at the atomic level, creating carefully structured transitions that can help phonons cross more easily. Some have even proposed using quantum wells and superlattices to control heat flow with unprecedented precision, opening the door to thermal transistors and heat-based computing. Perhaps most fascinating is how this challenge has led us to question our fundamental assumptions about energy transport. The classical view of heat as a continuous flow of energy breaks down at these boundaries, revealing the quantum nature of thermal transport. It's a reminder that even something as seemingly simple as heat flow contains hidden complexities that continue to surprise us. Back in our quantum computer, that invisible barrier you've hit isn't just threatening to melt a billion-dollar processor. It's revealing one of nature's most elegant paradoxes. Sometimes, understanding how the universe works isn't about watching things flow smoothly, but about studying where they mysteriously stop. And in that quantum traffic jam, we might just find the key to the next technological revolution. Dark energy acceleration. You're floating in the void between galaxies, watching as every point of light steadily drifts away from you, moving faster and faster with each passing moment. But here's the truly bizarre part. The farther away a galaxy is, the more rapidly it's accelerating away. It's as if some invisible force is stretching the very fabric of space itself, pulling the universe apart at its seams. And the most unsettling thing? We have absolutely no idea what's causing it. This cosmic acceleration was discovered in 1998, when two independent teams of astronomers were studying Type Ia supernovae, stellar explosions so consistently bright they serve as standard candles for measuring cosmic distances. The teams, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, expected to find that the universe's expansion was slowing down due to gravity's pull. Instead, they found something that shook physics to its core. The expansion was speeding up. The implications were staggering. For the universe to accelerate in its expansion, something must be pushing it apart. Some form of energy that works in opposition to gravity, growing stronger over vast distances rather than weaker. This mysterious force came to be known as dark energy, and it turns out to make up roughly 68% of everything in the universe. We're living in a cosmos dominated by something we cannot see, touch, or directly measure. But the real head-scratcher comes when we try to explain what dark energy actually is. Our best theory of gravity, Einstein's general relativity, allows for a cosmological constant, a kind of energy inherent to space itself. When physicists attempt to calculate how strong this cosmic energy should be, they arrive at a number that's wrong by 120 orders of magnitude. That's not just a small error. It's been called the worst theoretical prediction in the history of physics. The problem runs deeper than just a mathematical mismatch. Dark energy seems to violate our most basic intuitions about how forces should work. Every other force we know becomes weaker with distance. Gravity, electromagnetism, the strong and weak nuclear forces all follow this pattern. But dark energy does the opposite. Its effect grows stronger over vast distances, creating what astronomers call the cosmic web, a structure where galaxies cluster along invisible filaments, separated by ever-expanding voids. Some theorists have proposed alternative explanations. Perhaps gravity itself behaves differently on cosmic scales, or maybe we're observing the influence of parallel universes predicted by string theory. There's even a suggestion that we're seeing the effects of quantum entanglement operating across cosmic distances, though how this would work remains deeply unclear. The accelerating universe also raises profound questions about our cosmic future. If dark energy maintains its current strength, space will continue expanding faster and faster. Eventually, distant galaxies will recede so quickly that their light can never reach us. The observable universe will shrink, leaving our local group of galaxies alone in an endless void. It's a rather melancholic fate, our cosmic horizon slowly closing in around us like an inverse version of a black hole's event horizon. But perhaps the most fascinating aspect of dark energy is what it tells us about scientific discovery itself. Here, we have something that makes up the majority of our universe's energy content, fundamentally shapes its structure and destiny, and yet was completely unknown until just a few decades ago. It's a humbling reminder that our most basic assumptions about reality can be upended by careful observation and measurement. This connects to a broader pattern in physics. Some of our most important discoveries have come from studying things that don't quite add up. The slight wobble in Mercury's orbit led to Einstein's theory of relativity. The unexpected behavior of black body radiation gave birth to quantum mechanics. Now, the accelerating universe points to something even more fundamental about the nature of space, time, and energy that we've yet to understand. The quest to understand dark energy continues. New telescopes and surveys are mapping the cosmos with unprecedented precision, tracking the subtle ways this mysterious force shapes the evolution of cosmic structure. Each measurement refines our understanding while deepening the fundamental mystery at the heart of it all. As you float there between the galaxies, watching them drift away into the cosmic dark, you might reflect that their accelerating retreat represents one of the greatest puzzles in modern science, a reminder that the universe is not only stranger than we imagine, but stranger than we can imagine. And yet, in that very strangeness lies the promise of discovery, the possibility that in solving the riddle of dark energy, we might glimpse something profound about the fundamental nature of reality itself. EPR Correlation Problem. You're a quantum particle physicist working at a top-secret government facility, and you've just made a discovery that breaks everything you thought you knew about reality. Your morning began normally enough. Coffee, lab coat, firing entangled particles at detectors. But when you checked the measurement results, you found something impossible. Two particles, separated by kilometers, somehow instantly knew about each other's properties. No information could have traveled between them. It would have needed to move faster than light. Yet there it was, clear as day in your data. Either Einstein was wrong about the speed of light being the universe's speed limit, or reality itself wasn't what we thought it was. This bizarre quantum connection, known as the EPR Correlation Problem, emerged from a 1935 paper by Albert Einstein, Boris Podolsky, and Nathan Rosen. Their work aimed to expose what they saw as a fatal flaw in quantum mechanics, a theory Einstein helped create, but grew increasingly uncomfortable with. The paper described a thought experiment involving pairs of particles that seemed to violate a fundamental principle of physics: locality, the idea that objects can only be influenced by their immediate surroundings. Here's how it works. When certain particles are created together, they become entangled, meaning their properties are intrinsically linked. If you measure one particle's spin as up, its entangled partner will invariably be down, even if they're light years apart. The catch is that quantum mechanics says these properties don't actually exist until they're measured. They exist in a superposition of all possible states. This troubled Einstein deeply. How could measuring one particle instantly determine the state of another distant particle? Einstein called this spooky action at a distance, and believed it revealed quantum mechanics to be incomplete. He argued there must be hidden variables, properties built into the particles at creation that predetermined their behavior. To Einstein, the alternative was absurd. Either information was traveling faster than light, violating his theory of relativity, or the very notion of local reality, that things in one place can't instantly affect things somewhere else, was wrong. The debate remained largely philosophical until 1964, when physicist John Stuart Bell devised a brilliant mathematical proof. Bell's theorem showed that no local hidden variable theory could reproduce all the predictions of quantum mechanics. More importantly, he provided a way to test this experimentally. If quantum mechanics was correct, certain correlations between entangled particles would exceed what was possible with any local hidden variable theory. Decades of increasingly sophisticated experiments followed, culminating in a series of loophole-free tests in 2015. These experiments confirmed quantum mechanics predictions with unprecedented certainty. The correlations between entangled particles violated Bell's inequality exactly as quantum theory predicted, definitively ruling out local hidden variables. This leaves us with profound implications. Either we must accept that reality is fundamentally non-local, that distant objects can instantaneously influence each other, or we must abandon the idea that particles have definite properties before measurement. Both options challenge our basic intuitions about how the universe works. Some physicists have proposed even more radical interpretations. The many worlds interpretation suggests that when we measure entangled particles, we're actually splitting into multiple realities, each observing different results. Others propose that space and time themselves emerge from deeper quantum correlations, making apparent faster-than-light influences illusory. What makes the EPR correlation problem particularly fascinating is how it reveals the limits of our everyday intuitions. We evolved to understand the macroscopic world of cars and coffee cups, not the quantum realm where particles can be spookily connected across vast distances. Yet these quantum correlations are not just philosophical curiosities. They're the basis for emerging technologies like quantum cryptography and quantum computing. Back in your laboratory, staring at those impossibly correlated measurements, you're confronting the same profound questions that troubled Einstein. The particles in your experiment seem to be communicating instantaneously, defying our classical understanding of space, time, and causality. But perhaps the truth is even stranger. Maybe we need to abandon our cherished notions of local reality altogether, accepting that the universe is fundamentally more mysterious and interconnected than we ever imagined. Vacuum sound propagation. You're floating in the void of deep space, 100 kilometers from your damaged spacecraft, watching helplessly as its reactor core goes into catastrophic meltdown. The explosion should be deafening, yet as the blinding flash tears your ship apart, you experience the most unsettling silence of your life. In the vacuum of space, the thunderous destruction plays out in an eerie, perfect quiet that seems to defy everything we know about sound. This counterintuitive reality leads us to one of physics' most fascinating paradoxes. How can something as fundamental as sound simply stop existing? The answer lies in the very nature of sound itself, and it takes us deep into a world where our everyday experiences clash dramatically with the fundamental laws of physics. Sound at its core is nothing more than a wave of pressure moving through a medium. When someone speaks, their vocal cords create vibrations that push and pull the surrounding air molecules, creating areas of compression and rarefaction. These disturbances propagate outward, bouncing from molecule to molecule like an impossibly complex game of billiards. When these pressure waves reach our ears, they're interpreted as sound. The critical discovery about sound's nature came from Robert Boyle's pioneering work in 1660. His famous bell jar experiment demonstrated conclusively that sound requires a medium for transmission. Boyle placed a mechanical bell inside a glass jar and gradually pumped out the air. As the air thinned, the sound grew fainter until, in a near-perfect vacuum, it became inaudible, despite the bell's continued motion. This leads us to a profound realization. Sound isn't a thing in itself, but rather a behavior of matter. It's more accurate to say that matter can sound than to say that sound exists independently. This distinction becomes crucial when we consider environments like space, where the average density is around 1 atom per cubic centimeter, far too sparse for any meaningful pressure waves to form. But here's where things get truly mind-bending. While space is often described as a perfect vacuum, it's actually filled with various forms of matter and energy. Plasma waves, electromagnetic radiation, and even gravitational waves ripple through the cosmos. These phenomena share mathematical similarities with sound waves, leading to what scientists call cosmic sound. The European Space Agency's cluster mission detected what they termed space tsunamis, massive pressure waves in the thin plasma surrounding Earth. While these can't be heard in the conventional sense, they follow wave mechanics remarkably similar to atmospheric sound. Even more incredibly, when scientists convert the electromagnetic oscillations of celestial bodies into audio frequencies, they produce what's known as stellar seismology, allowing us to hear the songs of stars. This brings us to a deeper philosophical question. What exactly constitutes sound? If we define it purely as pressure waves in air, then space is indeed silent. But if we broaden our definition to include any oscillation that could theoretically be converted into audible frequencies, then the universe is actually a remarkably noisy place. The implications extend far beyond mere acoustics. The vacuum sound paradox highlights a fundamental truth about physical phenomena. They often exist on a spectrum rather than in absolute terms. Just as there's no such thing as a perfect vacuum in nature, there's no absolute silence. What we perceive as sound is merely one small slice of a vast continuum of vibrational energy permeating the universe. This understanding has practical applications in modern technology. Space agencies must account for vibrations transmitted through spacecraft structures, even though the vehicles operate in near-vacuum conditions. Communication systems in space rely on electromagnetic waves precisely because sound waves can't traverse the void. And our growing understanding of plasma waves has led to improved satellite navigation and space weather prediction. Returning to our unfortunate astronaut, watching their ship explode in silence, we can now appreciate the profound physics at play. The absence of sound in space isn't a failure of nature, but rather a perfect demonstration of its consistency. The silence speaks volumes about the fundamental properties of matter, energy, and the medium that binds, or doesn't bind, them together. In the end, the paradox of vacuum sound propagation reveals something remarkable. Our universe is governed by rules that are simultaneously simpler and more complex than our everyday experience suggests. The same principles that make space silent also give rise to the cosmic symphony playing out across the electromagnetic spectrum. We just need the right instruments to hear it. Event horizon radiation. You're falling through the event horizon of a black hole, but something impossible is happening. You're simultaneously in two places at once, existing as both intact matter and a scattered stream of radiation. And neither version of you is more real than the other. This quantum double life isn't just a thought experiment. It's at the heart of one of physics' most profound paradoxes, one that pits Einstein's relativity against quantum mechanics in a battle that threatens to unravel our understanding of how information behaves in the universe. The concept of event horizon radiation emerged in 1974, when Stephen Hawking published his groundbreaking paper, Black Hole Explosions, in the journal Nature. His calculations revealed something extraordinary. Black holes aren't entirely black. They emit a faint glow of radiation, now known as Hawking radiation, through a process that seems to violate fundamental laws of physics. At its core, this radiation arises from quantum effects near the event horizon, where virtual particle pairs constantly pop into existence. Normally, these pairs quickly annihilate each other, maintaining the conservation of energy. But at the event horizon, something peculiar occurs. One particle falls into the black hole while its partner escapes, becoming real radiation. The escaping particle appears to carry positive energy, while its infalling partner must therefore carry negative energy, reducing the black hole's mass. But here's where things get properly mind-bending. According to quantum mechanics, this radiation contains information about everything that ever fell into the black hole. Yet Einstein's relativity tells us that nothing, not even information, can escape once it crosses the event horizon. This contradiction is known as the black hole information paradox, and it's far more severe than it might first appear. From the perspective of someone falling into a black hole, nothing unusual happens at the event horizon. You simply pass through it, eventually reaching the singularity. But to an outside observer, you appear to stop at the horizon, gradually becoming redshifted and fading away, while simultaneously being encoded in the Hawking radiation that slowly carries away the black hole's mass. Both perspectives are equally valid, yet they're mutually exclusive. This leads us to the principle of black hole complementarity, proposed by Leonard Susskind and Gerard 't Hooft in 1993. It suggests that these contradictory descriptions are actually complementary. Both are true, but no single observer can see both versions of events. It's rather like quantum superposition on a cosmic scale, where a particle can exist in multiple states until observed. The implications extend far beyond black holes. This paradox challenges our most basic assumptions about the nature of reality. If information can be both preserved and destroyed, depending on your reference frame, what does that mean for causality, for determinism, for the very concept of physical law? The resolution might lie in quantum entanglement. In 2012, Ahmed Almheri and colleagues proposed the firewall paradox, suggesting that the event horizon might actually be a wall of intense energy, created by the breaking of quantum entanglement between particles inside and outside the black hole. This would preserve information, but violate Einstein's equivalence principle, which states that an observer falling through the event horizon shouldn't notice anything unusual. Some theorists, including Juan Maldacena, have proposed that the entire interior of a black hole might be a holographic projection of information stored on its surface. This holographic principle suggests that our three-dimensional reality might be encoded on a two-dimensional boundary, like a cosmic version of a hologram. The quest to resolve this paradox has led to extraordinary new ideas in theoretical physics. String theory, loop quantum gravity, and other attempts to reconcile quantum mechanics with gravity often find their strongest tests in trying to explain what happens at the event horizon. The ADS-CFT correspondence, a crucial tool in modern theoretical physics, emerged largely from attempts to understand this problem. Looking at the night sky, those tiny points of light seem so distant, so divorced from our daily experience. Yet in wrestling with what happens at their darkest edges, we're forced to confront the most fundamental questions about the nature of reality itself. Are space and time truly fundamental, or are they emergent properties of something deeper? Can information ever truly be destroyed, or does it simply take forms we can't yet comprehend? As you contemplate your quantum double life at the event horizon, remember that you're not just exploring an exotic corner of physics, you're probing the very foundations of reality itself. And perhaps that's the most remarkable thing about event horizon radiation. In the darkness at the edge of a black hole, we find light that illuminates the deepest mysteries of existence. Critical phase transition. You're standing in your kitchen, stirring a pot of water that's been simmering for hours, yet refuses to boil. The laws of physics seem to have taken a holiday. Despite the steady heat, the water maintains a stubborn 99.9 degrees Celsius, dancing right at the edge of its boiling point, but never quite making the leap. What you're witnessing isn't a malfunction of your stovetop or a glitch in reality. You've stumbled into one of physics' most remarkable phenomena, a critical phase transition. This peculiar behavior emerges from the delicate dance between order and chaos at the molecular level. In 1869, Thomas Andrews first documented this phenomenon while studying carbon dioxide under various pressures and temperatures. He discovered a precise point, now known as the critical point, where the distinction between liquid and gas phases simply vanishes. At this exact temperature and pressure, carbon dioxide exists in a state that's neither fully liquid nor fully gas, but rather a strange hybrid of both. The mathematics behind phase transitions was revolutionized in the 1960s by Kenneth Wilson, whose work on the renormalization group theory earned him the 1982 Nobel Prize. Wilson showed that near these critical points, systems exhibit universal behavior, meaning a pot of water approaching its boiling point shares deep mathematical similarities with a piece of iron losing its magnetism, or even a group of people approaching a collective decision. What makes critical phase transitions truly remarkable is their display of scale invariance. Take our pot of water. As it approaches the critical point, fluctuations in density occur at all scales simultaneously. Tiny droplets form patterns identical to larger ones, which in turn mirror even larger structures, creating a fractal-like cascade that spans orders of magnitude. This self-similarity isn't just mathematically beautiful. It's a fundamental signature of systems poised at the edge of transformation. The implications extend far beyond your kitchen. Critical phase transitions appear in surprising places throughout nature and society. Financial markets often exhibit critical behavior before major crashes, with fluctuations following eerily similar patterns across different timescales. Neural networks in our brains operate near critical points, allowing for optimal information processing and adaptation. Even the early universe likely underwent phase transitions as fundamental forces separated from one another during cosmic cooling. Modern research has revealed even more startling connections. In 2017, researchers at MIT discovered critical phase transitions in artificial intelligence systems, suggesting that deep learning networks undergo something akin to a phase change when they suddenly achieve competence at a task. The same mathematical framework that describes water molecules reorganizing themselves helps explain how neural networks reorganize their internal representations. The universality of critical phenomena raises profound questions about the nature of change itself. Why do so many seemingly different systems show identical behavioral patterns at their critical points? The answer lies in what physicists call relevant variables, the few key factors that dominate a system's behavior near criticality. Everything else becomes irrelevant, washing away in the face of the universal mathematical structures that emerge. This brings us to one of the most counterintuitive aspects of critical phase transitions. They represent points of maximum possibility. At the critical point, a system becomes exquisitely sensitive to small perturbations. The smallest nudge can cascade through the entire system, leading to large-scale changes. This property, known as critical sensitivity, helps explain why living systems often operate near critical points. It provides them with maximum adaptability and information processing capability. But perhaps the most profound implication of critical phase transitions is what they tell us about the relationship between the microscopic and macroscopic worlds. At critical points, individual components begin acting in concert, creating collective behaviors that can't be reduced to the properties of any single participant. The whole becomes not just greater than, but fundamentally different from, the sum of its parts. Looking back at your still simmering pot, you might see it differently now. That water isn't just refusing to boil, it's hovering at a point of infinite possibility, where the collective behavior of countless molecules creates something entirely new. In this light, critical phase transitions aren't just interesting physics. They're windows into the fundamental nature of change itself, showing us how transformation happens not just in water or magnets, but in everything from brains to markets to the cosmos itself. And perhaps, as you watch those final bubbles form, you're witnessing something more than just water becoming steam. You're seeing one of nature's most profound patterns, a pattern that connects the boiling of a pot to the thinking of a brain, the collapse of a market, and the birth of the universe itself. Thermodynamic arrow problem. You're floating in the void of space, watching in horror as your broken ship's components drift apart into an ever-expanding cloud of debris. Each piece tumbles away from the others, scattering into the darkness. But then, something impossible happens. The fragments begin to slow, stop, and reverse direction. Like a film playing backwards, every bolt, panel, and circuit board comes rushing back together, perfectly reassembling your spacecraft around you. While this scenario would technically be allowed by most laws of physics, you'll never see it happen. This apparent one-way nature of time, where broken things stay broken and disorder only increases, lies at the heart of one of physics' most perplexing paradoxes, the thermodynamic arrow of time. The mystery deepens when we examine the fundamental laws of physics, which are almost entirely time-symmetric. Whether you run them forwards or backwards, the basic equations governing particle interactions work equally well in both directions. Newton's laws, Maxwell's equations, even quantum mechanics, they all remain valid if you reverse time's flow. Yet our everyday experience tells a completely different story. Coffee cools down, but never spontaneously heats up. Eggs scramble, but never unscramble. Broken glass doesn't reassemble itself. This contradiction was first formally recognized by Ludwig Boltzmann in the 1870s as he developed statistical mechanics. He showed that while individual particle interactions are reversible, large collections of particles tend overwhelmingly towards states of higher entropy, essentially greater disorder. Boltzmann's H-theorem mathematically demonstrated this tendency, but it relied on probabilistic assumptions that seemed to sneak in time's arrow through the back door. The implications spiral outward into truly mind-bending territory. If the fundamental laws don't care about time's direction, why do we experience such a clear and consistent arrow of time? The answer appears to lie in the initial conditions of our universe. In 1889, Johann Joseph Loschmidt posed what became known as Loschmidt's paradox. If microscopic physics is time-symmetric, why can't we simply reverse all particle velocities and watch any system run backwards? The resolution hinges on an extraordinary fact about our cosmos. It began in an extremely low entropy state. The early universe was remarkably smooth and uniform, with matter and energy distributed very evenly. This is puzzling because it's an extremely unlikely condition. Roger Penrose calculated that the probability of such a low entropy initial state occurring by chance is roughly 1 in 10 to the power of 10 to the power of 123, a number so vast it defies comprehension. This cosmic initial condition creates what physicists call the past hypothesis, the assumption that the universe began in a very special low entropy state. As the universe evolves, it naturally tends toward higher entropy states, giving us the thermodynamic arrow of time we observe. But this merely shifts the mystery. Why did the universe begin in such an improbable configuration? The plot thickens when we consider black holes, which may hold crucial clues. Stephen Hawking's work on black hole thermodynamics revealed deep connections between gravity, entropy, and the direction of time. The surface area of a black hole's event horizon corresponds to its entropy, suggesting that the ultimate fate of our universe, likely an empty void populated by scattered black holes, represents maximum entropy. This connects to another fascinating implication. Memory and the flow of time are intimately linked through entropy. We remember the past, but not the future, because remembering requires creating records, which inevitably increases entropy. The very process of forming memories aligns with the thermodynamic arrow, explaining why we experience time's flow in one direction. Modern theoretical approaches have yielded new insights. The quantum Wheeler-DeWitt equations suggest that time might not be fundamental at all, but rather emerges from more basic quantum mechanical principles. Meanwhile, Sean Carroll and Jennifer Chen have proposed that our observable universe might be one half of a larger structure, with entropy increasing in both temporal directions from a central minimum. Looking back at your miraculously reassembled spacecraft, you'd realize that such an event isn't strictly impossible. It's just monumentally improbable. The atoms could theoretically happen to move in exactly the right way to reconstruct your ship, just as all the air molecules in a room could theoretically cluster in one corner. But the number of ways for things to be disordered so vastly outnumbers the ways for them to be ordered that we never observe such reversals. The thermodynamic arrow of time stands as a reminder that sometimes the deepest mysteries in physics aren't found in exotic mathematical theories or high-energy particle accelerators, but in the everyday asymmetry of how we experience reality. Every broken cup, every mixed paint. Cosmological horizon limit. You're trapped in an expanding bubble of space-time, and every second that passes, countless stars and galaxies slip irretrievably beyond your reach, their light stretching into oblivion, never to be seen again. This isn't science fiction. It's the reality we're living in right now, thanks to what physicists call the cosmological horizon limit, and it's creating a rather awkward situation for the future of astronomy. The universe is playing a cosmic game of keep away with us, and it's winning. In 1929, Edwin Hubble made the groundbreaking observation that distant galaxies appeared to be moving away from us, and the further away they were, the faster they seemed to be receding. This discovery led to one of the most profound realizations in scientific history. The universe isn't just vast, it's actively expanding. But here's where things get properly strange. This expansion isn't like an explosion where objects fly outward through space. Space itself is stretching. Think of it as if you're sitting on the surface of a balloon being inflated. As the balloon expands, every point moves away from every other point, not because they're moving across the surface, but because the surface itself is growing larger. Now, light has a speed limit, 299,792,458 meters per second in a vacuum. Nothing can travel faster than this cosmic speed limit, as Einstein's special relativity tells us. But the expansion of space itself isn't bound by this restriction. At sufficiently large distances, space can expand faster than light can traverse it, creating what we call the cosmological horizon. This horizon marks a fundamental limit to what we can ever observe or interact with. Objects beyond this boundary are expanding away from us faster than their light can travel toward us, meaning their signals will never reach us, no matter how long we wait. It's as if they've fallen over an edge in space-time, creating a cosmic blind spot that grows larger every moment. The implications are rather sobering. Based on current measurements of the universe's expansion rate, the Hubble constant, which is approximately 70 kilometers per second per megaparsec, our observable universe is shrinking in terms of what we can potentially interact with. Galaxies that are visible today will, in the very distant future, fade from view as they cross this cosmic horizon. But it gets more peculiar. Due to the finite speed of light, when we look at distant objects, we're seeing them as they were in the past. The light from the Andromeda galaxy, our nearest major galactic neighbor, takes about 2.5 million years to reach us. This means we're seeing it as it was when our ancestors were just learning to use stone tools. The further we look, the further back in time we see. This creates an interesting paradox. There are galaxies we can see right now that are already beyond our cosmic horizon. We're seeing them as they were billions of years ago, but if we try to send a signal to them today, it would never arrive. They're simultaneously observable and unreachable. The cosmological horizon limit also raises profound questions about the nature of scientific knowledge. There's a finite volume of space from which we can ever receive information, which means there's a fundamental limit to what we can know about the universe. It's as if we're living in a cosmic snow globe, where the edges of our observable universe are permanently out of reach. This has led to some rather unsettling philosophical implications. If we can never observe or interact with what lies beyond our cosmic horizon, can we meaningfully say that it exists? This touches on a fundamental question in the philosophy of science. What constitutes scientific reality? Is it only what we can observe, or does it include what we can deduce must exist, even if we can never see it? The horizon limit also impacts our understanding of the universe's future. As the expansion continues to accelerate, thanks to the mysterious force we call dark energy, more and more of the cosmos will slip beyond our horizon. In the very distant future, observers will see an increasingly empty universe, with nearly all galaxies having disappeared beyond the horizon, leaving only our local group of gravitationally bound galaxies. As we sit here, countless photons carrying information about distant corners of the universe are racing toward Earth, but they're in a losing battle with expanding space-time. Many will never make it. They're cosmic messages in bottles, destined to drift eternally in an expanding ocean of space, their contents forever unknown to us. So next time you look up at the night sky, remember that you're seeing a universe that's already partly gone, slipped away beyond a boundary that's as real as it is invisible. It's a humbling reminder that even in an age of remarkable technological advancement, there are some limits that no amount of innovation can overcome. These aren't engineering challenges waiting to be solved. They're fundamental properties woven into the fabric of reality itself. The cosmic horizon limit isn't just a distant academic concept. It actively shapes our current scientific endeavors. When astronomers plan their observations and design their telescopes, they must account for this cosmic deadline. Light from galaxies near our horizon is so redshifted by the expansion of space that it requires specialized instruments to detect. It's rather like trying to catch the final notes of a symphony that's eternally fading away. And yet, there's something oddly comforting about the horizon limit. It reminds us that mystery is built into the structure of our universe. No matter how advanced our civilization becomes, there will always be questions we cannot answer, places we cannot reach, and phenomena we cannot observe. The universe maintains its dignity by keeping some secrets permanently just out of reach. What makes this particularly intriguing is that different observers at different locations in the universe would have different cosmic horizons. An alien civilization in a galaxy a billion light-years away would see a completely different slice of the cosmos than we do. Their observable universe would overlap with ours, but wouldn't be identical. In a very real sense, each observer has their own unique universe, bounded by their own personal cosmic horizon. The cosmological horizon limit stands as one of physics' most elegant paradoxes. A boundary that exists everywhere but can be seen nowhere. A limit that grows larger while making our observable universe effectively smaller. A reminder that in our quest to understand everything, we must first understand that some things will forever remain beyond our grasp. Copenhagen Interpretation. You're standing in two places at once, both in your kitchen making coffee and simultaneously across town at work filing papers. This isn't a metaphor or thought experiment, according to one of physics' most widely accepted interpretations of quantum mechanics. This scenario isn't just possible, it's happening right now, just at a scale too small for you to notice. The fact that you only experience one version of reality is precisely what makes the Copenhagen interpretation so peculiar and profound. In 1927, at the 5th Solvay Conference in Brussels, Danish physicist Niels Bohr and German theoretical physicist Werner Heisenberg formalized what would become known as the Copenhagen Interpretation. Their radical proposal suggested that quantum systems exist in all possible states simultaneously until they're measured or observed. At that moment, the quantum system collapses into just one definite state. The mathematics behind this interpretation had already proven remarkably accurate through experiments like the double-slit test, where individual particles somehow travel through two slits simultaneously until they're measured, at which point they're found to have gone through only one. But the implications of these mathematics left physicists deeply uncomfortable. Take Schrödinger's famous cat thought experiment, proposed in 1935 specifically to highlight the apparent absurdity of the Copenhagen interpretation. A cat is placed in a sealed box with a device that may or may not kill it based on a random quantum event. According to the Copenhagen interpretation, until the box is opened, the cat exists in a superposition of states, simultaneously alive and dead. The act of observation causes this quantum superposition to collapse into one definite state. But what constitutes an observation? Does it require a conscious observer? If a tree falls in a quantum forest, does it exist in a superposition of fallen and upright states until someone looks at it? The Copenhagen interpretation is frustratingly vague on these points, leading Einstein to famously object that God does not play dice with the universe. Yet the mathematics continued to work with extraordinary precision. The quantum theories based on the Copenhagen interpretation have led to developments like transistors, laser technology, and quantum computers. The interpretation suggests that the fundamental nature of reality is probabilistic rather than deterministic. Things don't have definite properties until they're measured. This leads us to an even more startling implication. Consciousness itself might play a fundamental role in determining reality. If observation causes quantum systems to collapse into definite states, and consciousness is required for observation, then consciousness might be intrinsically linked to the basic fabric of the universe. This possibility has led some physicists and philosophers to suggest that consciousness itself might be a quantum phenomenon. The interpretation also raises profound questions about the nature of reality between measurements. If quantum systems exist in all possible states simultaneously until observed, what does this mean for our concept of reality when we're not looking at it? The Copenhagen interpretation suggests that unobserved reality exists only as a cloud of probabilities, a mathematical abstraction rather than a concrete thing. This connects to broader philosophical questions about the relationship between consciousness and reality. The philosopher George Berkeley argued in the 18th century that to be is to be perceived, that things only exist insofar as they're observed. The Copenhagen interpretation gives this idealist philosophy an unexpected scientific foundation. More recent interpretations of quantum mechanics have attempted to resolve these philosophical difficulties. The many worlds interpretation suggests that all possible quantum states continue to exist in parallel universes, while the pilot wave theory proposes that particles have definite positions guided by an underlying wave function. Yet the Copenhagen interpretation remains the most widely taught and applied interpretation in physics. Perhaps most remarkably, the interpretation suggests that the act of measurement doesn't just reveal reality, it helps create it. Your observation of an electron doesn't simply tell you where it is. Your observation participates in determining where it is. You're not just a passive observer of reality, but an active participant in its manifestation. So as you stand in your kitchen making coffee, consider that until you looked at your mug, its location existed only as a probability cloud. The act of observation collapsed those probabilities into the definite position you now perceive. And somewhere, in the quantum realm, versions of you might still be simultaneously performing all the actions you chose not to take, at least until someone looks. The coffee in your mug, like Schrödinger's cat, reminds us that the boundary between the quantum and classical worlds, between probability clouds and definite states, remains one of physics' most profound mysteries. The Copenhagen interpretation suggests that reality itself might be far stranger and far more dependent on consciousness than we ever imagined. Relativistic frame shifts. You're peacefully drifting through space in your perfectly spherical spacecraft when you notice something peculiar. Two identical space stations directly ahead, floating parallel to each other. As you drift closer, your instruments confirm they're exactly 100 meters apart. But there's a problem. According to the crew of each station, the distance between them is only 50 meters. Both crews have impeccable measuring equipment, and both are absolutely certain of their measurements. They can't both be right, can they? This delightful mess sits at the heart of relativistic frame shifts, one of physics' most mind-bending yet mathematically sound concepts. The key to this apparent impossibility lies in Einstein's special theory of relativity, published in his miraculous year of 1905. But to truly grasp why both space stations can be correct, we need to take a brief detour into the nature of reference frames. In classical physics, as formalized by Galileo and Newton, reference frames were straightforward affairs. If you're on a smoothly moving train and toss a ball straight up, it falls straight back down, both from your perspective and, accounting for the train's motion, from the perspective of someone watching from the platform. The mathematics linking these perspectives was simple addition and subtraction of velocities. But Einstein's work revealed something far stranger. His theory showed that space and time themselves aren't fixed and absolute. They're relative, warping and shifting based on motion. The faster an object moves relative to another, the more its time slows down and its space contracts along the direction of motion. This isn't just mathematical trickery. It's been confirmed countless times through precise atomic clocks and particle accelerators. Back to our space stations. Let's say they're moving relative to each other at an appreciable fraction of the speed of light. From your perspective, drifting perpendicular to their motion, you measure 100 meters between them. But from each station's perspective, the other station is moving at high speed, and according to special relativity, objects in motion experience length contraction along their direction of travel. The faster the relative motion, the more severe the contraction. The mathematics predicts exactly what we observe. Each station measures a shorter distance to its neighbor than you do. The 100 meters you measure contracts to 50 meters in their reference frames. Neither measurement is more correct than the other. They're both equally valid observations from different reference frames. This leads us to a profound implication. There is no universal now. Events that appear simultaneous in one reference frame might occur at different times in another. If you sent light signals to both stations that arrived simultaneously from your perspective, each station would insist the signals arrived at different times. The very fabric of space-time shifts and warps depending on relative motion. These frame shifts aren't just theoretical curiosities. GPS satellites must account for relativistic effects to maintain accuracy, as they move quickly enough relative to Earth for time dilation to become significant. Without these corrections, your phone's navigation would drift by kilometers per day. The implications extend beyond practical applications. Relativistic frame shifts challenge our intuitive understanding of reality itself. We evolved in a world where nothing moves fast enough for these effects to be noticeable. Our brains are wired for Newtonian physics, making it difficult to truly internalize these concepts. Yet mathematics and experiments consistently confirm that this is how our universe actually works. This raises fascinating philosophical questions about the nature of reality. If different observers can disagree about such fundamental properties as distance and simultaneity, what does this tell us about objective truth? Is there a true reality underlying these different perspectives, or are the perspectives themselves all we can meaningfully discuss? The answer seems to lie in what remains invariant across reference frames. While distances and times may shift, certain combinations of space and time measurements remain constant for all observers. The speed of light is the same in all reference frames, and the laws of physics themselves maintain their form. Perhaps these invariants, rather than our intuitive notions of space and time, represent a deeper reality. As you continue drifting past those space stations, their seemingly impossible measurements remind us that the universe is far stranger than our everyday experience suggests. The fact that such profound mysteries emerge from pure mathematical reasoning, only to be confirmed by careful observation, hints at an underlying order to reality that transcends our limited human perspective. Reality, it seems, cares little for our comfortable assumptions about how things should work. And perhaps that's the most beautiful part of physics. It consistently reveals a universe more fascinating than we could have imagined. Feline angular momentum. You're conducting a classified experiment at CERN's Large Hadron Collider when your research cat, Dr. Whiskers, somehow ends up floating in zero gravity above the particle accelerator. As you watch in horror, Dr. Whiskers begins to rotate, slowly at first, then faster and faster, reaching impossible speeds while maintaining perfect form. The truly bizarre part? She's breaking one of physics' most fundamental laws, and nobody can explain why. The infamous falling cat problem has perplexed physicists since the 1800s. When cats fall, they appear to violate the conservation of angular momentum, one of physics' most sacred principles. They can flip themselves over in midair without any external force, seemingly creating rotation from nothing. This apparent paradox reached scientific prominence in 1894 when French physiologist Étienne Jules Marey used chronophotography to capture the first detailed images of cats' aerial righting behavior. The conservation of angular momentum states that in a closed system, the total angular momentum must remain constant unless acted upon by external torque. Think of a figure skater. They spin faster by pulling their arms in, slower by extending them, but their total angular momentum stays the same. Cats, however, appear to generate rotation from scratch while falling, leading to decades of heated debate in the physics community. The solution lies in the subtle complexity of feline biomechanics. Cats utilize what physicists call the principal axis theorem by dividing their bodies into two separate rotating systems, the front and back halves. By twisting their flexible spine, they can redistribute mass around different axes of rotation. The front half rotates one way while the back half counter-rotates, maintaining zero net angular momentum while achieving overall reorientation. This principle extends far beyond our feline friends. In 1969, Soviet cosmonauts used the same technique to adjust their orientation in space without thrusters. The mathematics behind cat righting behavior now influences spacecraft design, robotics, and even quantum mechanics. The falling cat effect appears in surprising places, from the way DNA molecules unwind to how certain quantum particles change their spin states. But the deeper implications are even more intriguing. The cat righting reflex demonstrates how complex systems can exploit geometric phase effects. subtle mathematical properties that emerge from the way objects move through curved spaces. In 1984, mathematician Barry Simon coined the term geometric phase while studying quantum systems, but cats had been empirically demonstrating these principles for millions of years. The phenomenon connects to Emmy Noether's groundbreaking theorem linking conservation laws to symmetries in nature. While cats appear to break angular momentum conservation, they're actually revealing its deeper structure. Their motion preserves the underlying symmetry while exploiting the geometry of configuration space, the mathematical realm describing all possible ways a system can arrange itself. This leads us to a profound question. How many other apparent paradoxes in physics might be resolved by looking at them from a different geometric perspective? The history of science is filled with examples where seemingly impossible phenomena became clear once viewed through the right mathematical lens. The falling cat problem wasn't solved by discovering new physics, but by understanding existing principles more deeply. Recent research has revealed even more layers to feline angular dynamics. High-speed cameras have shown that cats can fine-tune their righting response based on fall height, utilizing air resistance and subtle aerodynamic effects. Some physicists now suggest studying cat biomechanics could provide insights into quantum control theory and the manipulation of complex quantum systems. Which brings us back to our rotating Dr. Whiskers at CERN. While cats can't actually generate unlimited rotation, as in our thought experiment, their real capabilities are perhaps even more remarkable. They've evolved a sophisticated biological system that exploits fundamental properties of geometry and physics in ways we're still working to fully understand. In mastering the art of falling, cats have become living demonstrations of some of physics' most elegant principles. As we observe Dr. Whiskers gracefully descending to the laboratory floor, we're reminded that sometimes the most profound insights come from the most familiar places. The solutions to physics' greatest paradoxes might not require exotic new theories or particles. They might be purring on our laps, quietly demonstrating fundamental truths about the nature of space, time, and motion. Spontaneous symmetry breaking. You're standing perfectly still in the exact center of a vast, perfectly circular frozen lake, surrounded by an endless expanse of identical snowflakes, falling in perfect symmetry around you. The scene is flawlessly balanced in every direction until you take a single step. That one movement triggers an elaborate chain reaction, sending ripples through reality itself, and suddenly the universe will never be quite the same again. You've just experienced spontaneous symmetry breaking, one of physics' most profound and counterintuitive phenomena that shapes everything from why we exist to why a pencil balanced on its tip must always fall. The concept emerged from the groundbreaking work of Yoichiro Nambu in the 1960s, though its roots trace back to Pierre Curie's symmetry principles from 1894. The basic idea seems to defy common sense. A system with perfect symmetry can spontaneously shift into an asymmetric state, even when nothing external appears to force this change. It's rather like a dinner party where everyone sits simultaneously at a perfectly round table with identical place settings. While the setup has rotational symmetry, the moment one person picks up their fork, the symmetry breaks. But the implications run far deeper than dinner etiquette. In quantum field theory, spontaneous symmetry breaking explains how particles acquire mass through the Higgs mechanism. The early universe existed in a state of perfect symmetry where all fundamental forces were unified. As it cooled after the Big Bang, this symmetry broke, rather like our frozen lake scenario, but on a cosmic scale. This breaking led to the differentiation of forces and gave particles their distinctive masses, enabling the formation of atoms, molecules, and ultimately, us. The mathematics behind this reveals something remarkable. Take our pencil balanced on its tip. In theory, it has perfect rotational symmetry and could fall in any direction. The equations describing its potential energy form a circular valley, with the balanced position as an unstable peak in the center. Any tiny perturbation, even quantum fluctuations, will cause the pencil to fall. But here's the crucial point. It must fall in some direction. The system is forced to choose a particular state from infinitely many equivalent possibilities. This phenomenon appears across vastly different scales and systems. In ferromagnetism, above the Curie temperature, electrons spins point in random directions, maintaining overall symmetry. But cool the material below this critical point, and the spins spontaneously align, breaking the rotational symmetry of the system. The same principle explains why crystals form with specific orientations from liquids that initially have complete rotational freedom. The philosophical implications are staggering. We're confronted with a universe that seems to require asymmetry to function, yet this asymmetry emerges from perfect symmetry. It's as if nature abhors not just a vacuum, but perfection itself. The very existence of structure, from galaxies to biological molecules, depends on these spontaneous breaks in symmetry. Modern physics has revealed even more profound connections. The Higgs field, confirmed by the discovery of the Higgs boson in 2012, permeates all of space in a state of broken symmetry. It's rather like an invisible cosmic molasses that gives particles their mass through continuous interaction. Without this symmetry breaking, all particles would be massless, zipping around at the speed of light, making atomic structure impossible. This leads us to a remarkable conclusion about the nature of reality itself. The apparent imperfections and asymmetries we observe aren't flaws in the cosmic design. They're essential features that allow complexity to exist. Our universe isn't built on perfect symmetry, but on the creative tension between symmetry and its breaking. Coming back to our frozen lake, that single step you took represents more than just movement. It embodies one of nature's most fundamental principles. The perfect symmetry of the untouched snow contained infinite potential. But only by breaking that symmetry could anything actually happen. In a peculiarly poetic way, it's the imperfections that make existence possible. And so we find ourselves in a universe where perfect symmetry must break for anything interesting to occur, where the very act of making a choice, any choice, creates asymmetry. Perhaps there's something profound in this, that the richness of reality emerges not from perfection, but from the beautiful necessity of its breaking. Hydrodynamic flow reversal. You're standing in your kitchen, casually pouring water into a glass when something impossible happens. The stream of water suddenly reverses direction, flowing upward from the glass back into the pitcher. Even more bizarrely, you notice that all the water in your sink is climbing up the drain pipe, and your morning coffee is ascending from your mug in perfect droplets. You've just stumbled into one of physics' most counterintuitive phenomena, hydrodynamic flow reversal, where the normal rules of fluid dynamics seem to break down entirely. This peculiar behavior was first documented in 1831 by Scottish engineer James Thomson, brother of the more famous Lord Kelvin. While studying fluid dynamics at the University of Glasgow, Thomson observed that under specific conditions, fluids could exhibit behavior that appeared to defy gravity and common sense. His initial paper, On Certain Curious Motions Observable at the Surfaces of Wine and Other Alcoholic Liquors, was largely dismissed by the scientific community as experimental error. The real breakthrough came in 1904 when Dutch physicist Johannes Diederik van der Waals expanded on Thomson's work in his seminal paper on phase transitions. Van der Waals demonstrated that at critical points, specific combinations of temperature and pressure, fluids can display behaviors that seem to violate our basic understanding of flow dynamics. These critical points create conditions where the distinction between liquid and gas phases becomes blurred, and normal fluid behavior breaks down. What makes flow reversal particularly fascinating is that it's not merely a laboratory curiosity. It's a phenomenon that plays a crucial role in everything, from weather patterns to industrial processes. When water flows through a pipe that suddenly narrows, it can create what's known as a hydraulic jump. This jump can, under precise conditions, cause the fluid to briefly flow in the opposite direction to the main current. Engineers must account for these effects when designing hydraulic systems, as unexpected flow reversals can lead to catastrophic failures. The mathematics behind flow reversal reveals an elegant connection to chaos theory. The Navier-Stokes equations, which describe fluid motion, contain hidden bifurcation points where stable flow patterns can suddenly split into multiple possible states. It's similar to how a perfectly balanced pencil standing on its tip might fall in any direction. Small perturbations can lead to dramatically different outcomes. This connects to a broader principle in physics, known as time reversal symmetry. While the fundamental laws of physics work equally well forward and backward in time, our everyday experience shows a clear arrow of time. We never see broken eggs reassemble themselves or spilled coffee jump back into cups. Yet flow reversal provides a window into how, under the right circumstances, systems can exhibit behavior that appears to run backward. The implications extend far beyond fluid dynamics. In quantum mechanics, there's a phenomenon called quantum flow reversal, where particles can tunnel backward through potential barriers. Cosmologists study similar effects in the behavior of matter near black holes, where space-time curvature can create regions where normal flow dynamics break down completely. Recent experiments at the Massachusetts Institute of Technology have demonstrated flow reversal in superfluids, exotic states of matter that flow without friction. In 2019, researchers created microscopic channels where superfluid helium exhibited spontaneous flow reversal, moving against an imposed pressure gradient. This work has opened new possibilities for developing quantum devices that exploit this counterintuitive behavior. The practical applications are surprisingly widespread. Aircraft designers use flow reversal principles in thrust reversers to help large planes slow down after landing. Climate scientists study flow reversal patterns in ocean currents to better understand how global warming might affect marine circulation. Even medical researchers are investigating how flow reversal in blood vessels might be harnessed for targeted drug delivery. Perhaps most remarkably, flow reversal teaches us something profound about the nature of physical laws. What we consider natural or impossible often reflects our limited everyday experience rather than fundamental restrictions. Just as Einstein's relativity showed that time can flow at different rates, hydrodynamic flow reversal reveals that even something as basic as the direction of flowing water isn't as fixed as we might assume. So the next time you're pouring water into a glass, remember that in the strange realm of physics, even this simple action contains hidden complexities. Under the right conditions, that stream of water really could flow upward, not by magic, but by the remarkable principles that govern our physical world. Cosmic background radiation. You're floating in the darkest void imaginable, billions of light years from the nearest galaxy, yet everywhere you look, there's a faint ethereal glow, the afterglow of the Big Bang itself, still lingering after 13.8 billion years. This ancient light, reaching your eyes from every direction simultaneously, is telling you something remarkable. You're literally seeing the universe as it existed when it was just 380,000 years old, a mere infant in cosmic terms. This omnipresent radiation wasn't discovered by pointing massive telescopes into deep space or through complex theoretical predictions. Instead, it was found by accident in 1964 when two Bell Labs engineers, Arno Penzias and Robert Wilson, were trying to eliminate an annoying background noise in their radio antenna. They cleaned out pigeon droppings, checked all their equipment, and still couldn't explain the persistent signal that seemed to come from everywhere at once. What they'd stumbled upon would turn out to be one of the most important discoveries in the history of cosmology. The cosmic microwave background radiation, as we now call it, is effectively the universe's baby picture. When the universe was young and incredibly hot, it was filled with a dense plasma of electrons, protons, and photons all bouncing off each other constantly. Light couldn't travel far before being scattered, making the early universe effectively opaque. But as the universe expanded and cooled, something dramatic happened around 380,000 years after the Big Bang. The temperature dropped enough for electrons to combine with protons, forming neutral hydrogen atoms. This moment, known as recombination, changed everything. Suddenly, photons could travel freely through space without being scattered. The universe became transparent, and that first light has been traveling through space ever since. What started as brilliant, high-energy radiation has been stretched by the expansion of the universe, cooling down to microwave wavelengths, a mere 2.7 degrees above absolute zero. But here's where things get truly strange. This background radiation is almost perfectly uniform across the entire sky, varying by only about 1 part in 100,000. This extraordinary uniformity presents a puzzle that has haunted cosmologists for decades. Regions of space on opposite sides of our observable universe couldn't possibly have been in contact with each other. There hasn't been enough time since the Big Bang for light to travel between them. So, how did they end up with virtually identical temperatures? This conundrum led to the development of inflation theory in the 1980s, proposed by physicist Alan Guth. The theory suggests that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, inflating faster than the speed of light. This would explain the uniformity we observe, as all regions of the observable universe would have been in contact before inflation drove them apart. The tiny variations we do see in the cosmic background radiation are equally fascinating. These minute differences in temperature represent quantum fluctuations from the early universe, blown up to cosmic scales by inflation. These slight irregularities became the seeds of all cosmic structure, the galaxies, galaxy clusters, and the grand cosmic web we see today. You're literally looking at the blueprint from which our universe was built. What's particularly elegant about cosmic background radiation is how it serves as a kind of ultimate horizon of knowledge. We cannot directly observe anything from before this radiation was released. The universe was opaque then. It's as if we're standing on the shore of a cosmic ocean, with the waves of this ancient light lapping at our feet, bringing us messages from the edge of time itself. The technology we use to study this radiation has come a long way since Penzias and Wilson's accidental discovery. Satellites like COBE, WMAP, and Planck have mapped the radiation in exquisite detail, revealing not just its temperature variations, but also its polarization patterns. These observations have helped confirm predictions of inflation theory and have given us the most precise measurements of the universe's composition, showing that ordinary matter makes up only about 5% of the cosmos, with dark matter and dark energy accounting for the rest. As you float here in the void, bathed in this ancient light, you're experiencing something profound. Every photon of this radiation has been traveling for 13.8 billion years, crossing most of the observable universe to reach you. This light was released when the universe was 1,000 times smaller than it is now, and it carries within it the answers to some of our deepest questions about cosmic origins. The mere fact that we can detect and study this radiation, this whisper from the infant universe, stands as one of humanity's greatest scientific achievements, turning the entire observable universe into our laboratory. Quantum state correlation. You're standing in two places at once, literally. Not metaphorically, not theoretically, but actually existing in two distinct locations simultaneously, a kilometer apart. Your left half is in one lab, your right half in another, and yet somehow you're perfectly fine. In fact, you're about to help conduct the most important physics experiment in history, the problem. Your two halves are exhibiting behaviors that, according to Einstein himself, should be completely impossible. This isn't just a thought experiment, it's precisely the kind of quantum correlation that had Einstein calling it spooky action at a distance. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper that would become known as the EPR paradox, arguing that quantum mechanics must be incomplete because it seemed to allow for instantaneous communication between particles, violating the speed of light limit. The heart of their concern lay in what we now call quantum entanglement. When two particles become entangled, their quantum states become correlated in such a way that measuring one instantly tells you about the other, no matter how far apart they are. It's as if you had two coins that always landed on opposite sides, even if they were flipped on different planets. But this isn't just about coins or simple measurements. the mathematics tells us something far more profound. These correlations are stronger than anything we can explain with classical physics. John Bell proved this in 1964 with his famous inequality theorem, showing that no local hidden variable theory could reproduce the predictions of quantum mechanics. To understand how bizarre this is, let's return to your split self. Your left half measures the spin of a particle in Lab A, while your right half measures its entangled partner in Lab B. The instant, and I mean truly instant, with no time delay, your left half observes spin up, your right half will observe spin down. There's no signal passed between the particles, no hidden message, no secret variable determining the outcome beforehand. This correlation is so perfect, so instantaneous, that it seems to defy our most basic understanding of causality. It's as if the universe itself maintains a kind of bookkeeping that transcends space and time. The particles aren't communicating. They're manifesting two aspects of a single, unified quantum state that simply doesn't recognize spatial separation as we understand it. The implications stretch far beyond particle physics. These quantum correlations form the basis of quantum cryptography and quantum computing. When we generate encryption keys using entangled particles, any attempt to eavesdrop disturbs the delicate quantum state, immediately revealing the intrusion. It's nature's own perfect security system. But the philosophical implications are even more staggering. If particles can maintain instantaneous correlations across any distance, what does this tell us about the nature of space itself? Some physicists, like Juan Maldacena, suggest that space-time might be emergent, a kind of illusion arising from more fundamental quantum correlations. Your split self in the two labs isn't just measuring particles. You're witnessing the fundamental interconnectedness of reality. The fact that you can exist in two places while maintaining perfect correlation mirrors the quantum state itself. It challenges our deepest assumptions about locality, causality, and the nature of reality. What Einstein found so troubling wasn't just the apparent faster-than-light influence. It was the implication that reality itself might be fundamentally non-local. The mathematics suggests that separated particles aren't really separated at all. They're manifestations of a deeper unity that our classical intuitions struggle to grasp. Modern experiments have confirmed these correlations with increasing precision. The most recent tests, conducted by teams like Anton Zeilinger's, have closed nearly every conceivable loophole in Bell's theorem. The universe really does exhibit these spooky correlations, whether we're comfortable with them or not. Your split self, maintaining perfect correlation across a kilometer of space, embodies the same mystery that lies at the heart of quantum mechanics. Just as your two halves remain part of a single consciousness, entangled particles remain part of a single quantum state, undivided by space or time. As you complete your measurements in both labs, you're not just conducting an experiment, you're participating in one of nature's deepest mysteries. The perfect correlation between your actions, like the perfect correlation between entangled particles, points to a reality far stranger and more unified than our everyday experience suggests. Perhaps Einstein's discomfort with quantum correlations wasn't just scientific conservatism. It was a recognition that these phenomena force us to radically revise our understanding of reality itself. As you stand in both labs, simultaneously observing these impossible correlations, you're not just split.